everyone, welcome to Leetcode Simplified. Today we're walking through the two-sum problem. Clean and efficient way to solve this problem using a simple idea that you will see over and over again in coding challenges. Let's get right into it. So here the problem goes like this. Given an array called num and a number called target. Guarantee there are two different numbers in this array that will add up to the target. Find them and return their indices. For example, given this array and the target number 9, so you should return the indices of 2 and 7, which is 0 and 1. So here's the idea. Keep a dictionary called hashmark that store the numbers we already seen along with their indices when we traverse through the array. Because for each number we looked at, we can always ask, what number should we need to pair with this number to reach the target sum? So we call that number the complement. It's just a target number minus the current number we are visiting. Let's say we are at the current number 7 and the target is 9. The complement of 7 is 2. Check in the dictionary. Have I seen this number 2 before? If yes, there's the answer. 2 and 7 are the two numbers that add up to 9, and we will return their indices, which is 0 and 1. If not, we store the number and we keep going. Let's head over to Python. Map. So we're going to loop through this array using enumerate, a built-in Python function to retrieve the index of the number together with the number. For the index and the number itself, in the object enumerate of nums, calculate the potential complement, and we save it into the complement variable. If the complement in the num map dictionary, return the index of the complement and the index of the current number. Now, if the complement isn't in the dictionary, we need to store the current number with its indexes so we can use it later if needed. Let's submit our solution to Leetcode. Moment of truth. Boom, accepted. That's our solution to the two-sum problem. This approach is powerful because it lets us find the answer as we loop through without checking every pair of numbers. The key is using the dictionary to remember what we've seen. So anytime you're solving problems that ask about finding pairs or checking if something exists based on earlier values, this pattern is worth remembering. That's it for a two-sum problem. If this helps, subscribe to Leetcode Simplified for more tutorials like this one. Thanks for watching and keep practicing. Hi everyone, welcome to Leetcode Simplified. Today we're solving two classic palindrome problems, and we do it in a clean and efficient way by converting the problem into a form that's easy to check. Let's get right into it. Palindrome number. Given an integer x, return true if x is a palindrome, meaning it reads the same forward and backward, and false otherwise. 1 to 1, read backward, 1 to 1, the same. Minus 1 to 1, not the same as 1 to 1 minus. 1, 0 is different from 0, 1. It's not a palindrome. So what is the idea? Convert the number to a string, which is easy to check whether it's equal to its reverse. Let's go to Python. Convert the number to the string, save it into a variable called string underscore x, and compare that string is the same as its reverse, and whatever return true or false. That's how simple it is. Submitted to Leetcode. Boom, accepted. Let's move on to Leetcode 125, valid palindrome. Very similar to the last one. Given string s, determine if it's a valid palindrome. But here's the catch. You need to ignore non-alphanumeric characters and treat the uppercase and lowercase the same. For example, giving you this string, after you convert it, it becomes this string, and reverse reading is the same. So it's a palindrome, so the output returns true. It's not the same for this string, race a car. After you do the conversion, you read it backward, not the same, so it's false. Let's write that in Python. Go through every character, do the conversion. For every character in S, if that character is alphanumeric, then we'll lowercase that character. And then join all the characters in string S without space. So now the string s become this string. Save it in a variable called clean. Now we just compare each clean string is the same as its reverse, and whatever valuation becomes, return it. Okay, submit it to Leetcode. Boom, accepted, super clean. So what's the key takeaway? The main idea in both problems is this: one, you convert your input into the right format. Checking for palindrome becomes really easy, just compared to its reverse. This pattern, transform then compare, come up a lot in string problems. That's it for today's video. Hope it's helped. Give it a thumbs up and subscribe to Leetcode Simplified for more and quick tutorials just like this one. Thanks for watching and keep practicing. Do you know how to convert Roman numeral to the normal number system that we use today? Did you know there's a special rule in Roman numerals that actually goes against how we naturally think about numbers? Today we're walking through the Roman to integer problem. We will explore a clean and clever way to convert it into an integer using a simple idea that handles all cases correctly with just one pass through the string. Let's get right into it. Given a string that represents a Roman numeral, convert it to its integer form. Here's the idea that gets the job done in the optimal way. Go to the Roman numeral from right to left. For each character, compare its value with the previous one. If it's larger, add. If it's smaller, subtract. Let's walk through these following examples step by step. Scan through every single character from right to left. Compare its value to the previous one. If it's larger, add. If it's less, we subtract. Given this string, scan from right to left. The first one is value 1. Its previous, which we assume is 0, so we add 1. The next one, also 1 is the same, so we also add. Now go to the last character, its also value is 1. The same, the previous one, so we also add. So the total 1 plus 1 plus 1 is 3. These values start with I. Its 1 is greater than its previous 0, so plus 1. Next one is also another 1, so we add. The third one, 1, same thing is 1, so we also add. Now V value is 5, greater than 1, add. L value 50, greater than its previous 5, add. The total is 58. How about this one? We start with V, 5, greater than 0, we add. I, 1 less than 5, then we subtract it. C is 100, greater than previous value is 1, add. Move to the next one. X is 10, smaller than its previous value, 100, subtract. And go to M, 1000, greater than its previous value, 10, add. Now C is 100, less than its previous value, 1000, subtract. And then the last one is M, 1000, greater than 100, add to the overall value. Overall total is 1994. We just did convert this string to its integer values. Okay, so given this, we're going to copy the symbol and its values. Create a dictionary using the given information. So we call it dictionary Roman equal, and then I'm going to paste it in. I'm going to make a dictionary. That is our dictionary. Initialize the total with 0. We're going to compute that number and return that. At the end, it's 0 for now. So for each character from right to left, we retrieve the value of that character and we save it in cur. If cur is greater than equal the previous values, initialize it with the value 0. So we just add to the overall total. L is smaller. Now this is the crucial step that goes against our instant processing in the mind. Subtract the current value from the overall total. Update the previous values with the current value before we move on. Return the total. Alright, submit it to Leetcode. Boom, accepted. This approach works in time on and is very efficient for any valid Roman numeral input. That's it for Roman to integer problem. If this helped, give it a thumbs up and subscribe to Leetcode Simplified. Hi, I'm Alan. Welcome back to Leetcode Simplified, where we simplify coding problems and breaking them into simple steps. Today, we're solving Leetcode 14, longest common prefix. It's a classic string problem that often shows up in interviews, giving a list of strings. Find the longest common prefix amongst them. If there are no common prefix, return an empty string. For example, this list of strings, common prefix among all of them is FL. FL stock right here in this string. FL stock right here. FL also stock in this string. So FL is the longest common prefix amongst all the three strings. This list of strings, this start with D, this start with R, this start with C, have no common prefix to start with. Return an empty string. Here are the steps. If the list is not empty, we assume the first string as the prefix and check if all the strings start with it. If not, shorten the prefix and try again until all the strings in the list start with that final prefix. At this point, the final prefix is the longest common prefix of all the strings in the list. At any time while we performing the process of shortening the prefix and the prefix become empty, terminate the process immediately. No common prefix. Let's go through the below example step by step. Assume the first string is the prefix. Flower is our prefix now, and we're going to use it to test against each and every string in the list. Test it with flow. Flow start with flower? No. So we chop the last character from the prefix and try again. Flow start with flowy? No. Chop the last character from the prefix. String flow start with prefix flow? Yes. Move on to the next string and test it with prefix flow. Fly start with flow? No. Then we chop the last character from the prefix and try it. Does fly start with flow? No. Chop the last character from the prefix, test it with fly. Does fly start with FL? Yes. Go to the next one, but we have no more string to test. The current prefix right now is FL, and that will be the common prefix amongst all the three strings. Now take a look at this example. First, assume the first string is the prefix. Save it to the variable called prefix. So dog is our prefix right now. Use dog to test against each and every strings in the list. Shorten the prefix accordingly. Let's test it with race car. Does race car start with dog? No. Okay, how about this one? Does race car start with do? No. How about this one? Does race car start with D? No. Chop. In every step, after we chop the last character, always check if the prefix is empty. Currently it is. The prefix right now is empty. Immediately terminate the loop and return the empty string. Now let's walk through the actual code together in Python. First thing first, check if the list is empty. Return empty string. Get the first strings at position 0 and we assume that is the answer. Prefix. Test this against all other strings in the list. Scan through every other string in the list starting from the second one. If the current string not start with the prefix, we will chop the last character from the prefix. And if we want to do it again, why is the string not starting with the prefix? If prefix is empty and the loop return the empty string. At the very end, we return the final common prefix among all the strings in the list. Now let's submit it. Voila! Accepted. And that's it for today. We use a simple while loop and a few string comparisons. Get the job done. We assume the first string is the prefix. Keep trimming it down until it's common amongst all the other strings. This algorithm avoids complex comparison. And that's it for today. For the longest common prefix problem, if this helped you, give it a thumbs up and subscribe to Leetcode Simplified. Welcome back to Leetcode Simplified. We break down problems into clear and simple steps. Today we're solving problem 20, valid parentheses. Given a string S contains only parentheses, determine if it's valid. We need to check if the brackets are closed in the correct order. This is perfect for a stack. Here is a simple idea. Go through each character. If it's an opening bracket, push it onto the stack. If it's a closing bracket, pop the stack. If it's not empty, and check if it's the pair with the closing bracket we are at. If we are able to read through the last character, return true. If the stack is empty, that means every open bracket has a matching closed bracket in the correct order. Let's take a look at a few examples. When we see an open bracket, push it into the stack. We go to the closing bracket, pop this one out, and find its matching. Its matching pair, this one is at the same as that one. So return true. Next one, opening bracket, pushes into the stack. Closing bracket, then we pop this one out and find its matching pair, which is this, same thing as that. Go on to the next one. It's open bracket, push it into the stack. Move on, closing bracket, then we pop this one out, find its matching pair, compare it, same thing as that. Go on, next one, open bracket, push it into the stack. Go on, closing bracket, then we pop this item. Its matching pair is that, same as this. At this point, it will read through all the characters and the stack's empty. The string is valid parentheses. This one, first one is open bracket, push to the stack. Closing bracket, pop the stack. Its matching pair, this one. Is this the same as that? No. Immediately return false. Last one, open bracket, push it into the stack. Another open bracket, push it into the stack. Closing bracket, pop this one out. Its matching pair is this, the same. Then move on. This character, closing bracket, pop the stack. This item is matching pair, same as that one. No more character to read, and the stack is empty. The string is a valid parenthesis. If we're clear on the example, let's head over to Python. So the first thing is to build a dictionary so we can refer to it anytime we want. Call it a pair. Create a stack. Now scan through every character in string S. If the character is the open bracket, this, push into the stack. If the stack is empty, return false immediately. If the stack still have an item to pop out, it will pop out that item. Find its matching pair. Check if it's the same as the closing bracket we are reading right now at the moment, and if it's not, also immediately return false. Otherwise, if it's the same, move on to the next character. Repeat, iterate until no more character to read. Return true. If nothing in the stack, let's submit it to Leetcode. Finger crossed. Successful. Accepted. That was valid parentheses. Welcome back to Leetcode Simplified, where we make coding problems easier to understand, one step at a time. Today we're solving Leetcode 21, merge to sorted list. Classic linked list problem that tests ability to manipulate pointers and build a new list. Given two sorted linked lists, merge them by splicing together the node of the two lists. Here are the steps. Use a dummy node and a tail pointer to walk through the two lists. Compare values and connect the smaller one to the merged list each time. Once one list is empty, attack the leftover nodes from the other list. Return dummy.next as the head of the final merged list. Let's look at the example below and watch how the pointer do the magic. When it comes to linked list, seeing is understanding. The problem gives us two pointer, list 1 and list 2, that point to the head nodes of the two sorted linked lists. Create a list node object and set pointer dummy to point to it. I also create pointer tail that also point to the same list node as dummy. So far, list 1 point to the head node of the first list, list 2 point to the head node of the second list. Dummy and tail point to dummy list node. Now look at the two head nodes, compare the values. If value in the list 1 is less than or equal value list 2 point the next pointer up tail to list 1. Advance list 1 pointer. Move tail to the node it just connected to. Repeat the process to look at the two head nodes 1 and 3. Point the tail next to 1. Advance list 2 pointer to the next node in line 2. And point tail pointer to the node it just connected to. Now node 3 is the head of list 1 and node 2 is the head of list 2, which is smaller. So point tail next to node 2. Advance list 2 pointer to the next node in line. Advance tail to the node it just connected to, which is 2. Repeat. So node 3 is the current head of list 1. 4 is the current head of list 2. So tail will point next to node 3, which is smaller. Advance list 1 pointer to the next node in line 4. After that, tail will advance to the node it just connected to, node 3. Repeat. List 1 head is node 4. List 2 head also 4 equal. I will point tail next to node 4 in list 1. And now list 1 will advance to none. Tail move to the node it just connected to, node 4 in list 1. This time process will not continue because one of the list is none. Loop terminated. Point tail next to whichever list is not none, list 2. Finally, return dummy.next with point to this node. Node 1, the head of the merged linked list, which is connect 1 to 1 to 2 to 3 to 4 to 4. If everything is clear so far, let's write the Python code to make it happen. First, make a list node, make a dummy pointer, point to it. Then create another pointer called tail, which also point to the same list node as dummy. While list 1 and list 2 exist, do the following. If list 1 value less than or equal list 2 value, set tail next point to the same node that list 1 point to. Then move list 1 to point to its next node. Else, do the same. Tail next point to list 2 and advance list 2. After connect tail to the smaller node and move to the next node available, now it's time for tail to advance to the node it just point to. Point tail next to list 1 if list 1 still exists, else list 2. Finally, return the merged list dummy.next. And we're done. Okay, let's submit to Leetcode. Moment of truth. Whoop, typo. List 1 point to the next node. Try again. Boom, accepted. We successfully merged two sorted linked lists using pointer manipulation. Hi friends, Alan here, and this is Leetcode Simplified, where we'll make problems easy to understand. Today's problem, Leetcode 26. Remove duplicate from sorted array. Given a sorted array, remove duplicate in place. That means no extra space allowed. Modify the array directly that the first k element are unique elements and return k. Let's understand the problem quickly. If the input is this array, modify it to be like this. The output should be two unique elements in this array. How about this input array? We're going to modify it in place and it will become this, and we return 5 unique elements. The key trick here, the array is already sorted, so all duplicates will always be next to each other. So you have 0 0 1 1 1 2 2 3 3. Here's the idea to tackle this problem. Use pointer I to keep track of the position of the last unique element, and pointer J to scan through all the elements and compare it with the last unit element. If it's different, congratulations, we just found another unique element. Copy it to the right position of the last unique. Here comes the fun part, a visual walkthrough. watch how the arrays get modified as pointers I and j move through it step by step. First of all, set up I is position of the first unique element. So 1 is the first unique element. We will go through every order. When j at position 1, 1 is the same as 1 at position I. If the same, then advance j to the next element without doing anything. Now 2 at position j is the same as 1 at position I. No, congratulations, we just found another unique element. Advance I and copy 2 to that position. At this time, the loop ends because no more element. Position I is 1, return 2, which is I plus 1. Next example, this element 0 at position I is the first unique element. We're going to use pointer j to scan through all the elements and compare with the last unique element 0. 0 at j is the same as 0 at I. Do nothing. Advance j to the next position. 1 at j different from 0. Then we're going to advance I to the next one and copy 1 to that position. Next repetition, advance j to the next position. 1 at j is the same as 1 at I. Do nothing. Continue, advance j to the next position. 1 at j, the same thing as 1 at I. Do nothing, advance j again. Now 2 at j is different from 1 at I. So we just found 2 is a new unique element. Then advance I to the next position and copy 2 over there. Now advance j to the next position. 2 at j, the same thing as 2 at I. Do nothing, advance j again. 3 at j is different from 2. So 3 is the new unique element. Advance I to the next position and copy 3 there. Now advance j to the next position. 3 at j is the same as 3 at I. Do nothing. Advance j to the last position. 4 at that position is different from 3. Then 4 is a new unique element. Then advance I to the next position and copy 4 there. This time the loop is end. J already go to the end of the array. I is 4, return 5. If you are with me so far, great. Let's turn the idea into actual Python code. First, set the position of the first element I equals 0. So the first unique element is at the first position. You pointer j to scan through the array from second position to the end of the array. If the elements at j is different from the elements at I, congratulations, we found the new unique element. Advance the position of the last known unique elements and copy the current elements to that position. At the end, when j went through all the elements, return I plus 1. The first I plus 1 element are unique elements. Done. Let's submit to Leetcode. Oh, accepted. Perfect. Clean, fast, and no extra memory needed. If that helps you see it a little more clearly, subscribe to this channel. Welcome back. Alan here with another episode of Leetcode Simplified, where we break down problems the easy way. Today we're tackling Leetcode 27. Remove element. Modify an array and remove in place all the occurrence of val and return how many number of non-val, and we need to do it in place. Let's see, you have this array and we need to remove 3. Only keep the 2, put it in front, and another 2 non-val we're gonna put it in front, and we return how many of them? 2 element, not 3. Let's take a look at another array. So this val is 2, so non-val is 0, keep it in front. 1 is non-val, we're gonna keep it in front. 2 is val, we skip that. 2, skipped it. And 3, non-val, keep it in front. 0 is non-val, we're gonna keep it in front. 4 is non-val, we're gonna keep it in front. And 2, don't do anything about that one. So how many non-val elements in front of the array? The answer should be 5. The approach: use J to scan through each element, and if it's non-val, copy it to the position I and advance I. At the end, I will be the number of the non-val element in the array. Alright, let's make this even clearer. Animate this step by step. Watch how our two pointer I and J slide through the array and clean things up as they go. First, initialize I at this position to keep all the non-val elements. Traverse the array with J, and whenever the element at the J position is non-val, copy it to the I position and advance I. Otherwise, the value at J position is the same as val. Move to the next iteration, advance J to the next element, and compare. 2 is different from 3 at position I. Then copy 2 at the I position and advance I. Next iteration, J go to the next element 2, which is non-val, different from 3. Then we copy 2 to the I position and advance I. Next iteration, advance J to the next and last element in the array. Its value is 3, is the same as the value we don't want. Terminate the loop because J is at the end. At this point, how many non-val elements? 2 and 2, which is 2. So we return 2. Move on to the next example. First, initialize I is where to place the non-val elements, and J the index to traverse the array. If the element at J is non-val, in this case 0 is non-val, copy 0 to the I position, advance I, repeat J go to the next element, 1 non-val, so we'll copy 1 to the I position and advance I. Next repetition, advance J, 2 value we don't want, do nothing. Next iteration, advance J 2, the value we don't want, advance again. J now E3, non-val, we copy 3 to the position I and advance I. Next repetition, advance J 0, which is a non-val, then copy it to the position I and move I to the next position. Next repetition, J go to 4 non-val, so we copy 4 to the I position and advance I. Next, move J to the last position in the array, 2, the value we don't want, do nothing. This time, the loop ended, no more element. So I is the number of non-val elements in the array. Return I, which is 5. Got the idea? Awesome. If everything makes sense so far, let's translate this logic into Python. First thing first, initialize I at the position where we start storing the non-val element. Then traverse the array. If the values at J position is non-val, then we copy that value to the I position and advance I. At the end, no more element, then return I, the number of non-val elements in the array that we kept in the front. Done, clean, simple and in place. Let's get ready to rumble. Submit. Boom, accepted. That's a fast, clean solution with no extra memory. Just 2 pointers and solid logic. If this walkthrough helped you out, please subscribe. We will go through each and every Leetcode problem step by step, line by line. Hi everyone, welcome back. Alan here with another episode of Leetcode Simplified, where we break down problems the easy way. Today we're tackling Leetcode 28, finding the first occurrence in a string, given 2 strings, needle and haystack. return the index where needle first appear inside haystack. If it's not there, return -1. Let's say you have sad but sad and the needle sad. So sad first appear at position 0, so we return 0. Whereas little appears in Leetcode, none, so we return -1. The popular technique we're using here is often called the sliding window approach, where we will slide a window the same size of the needle across the haystack, checking each substring for a match with the needle, and as soon as we find one, return its starting position. To make this clearer, let's animate step by step. Let's say the needle is TSA. Find TSA in the string sad but sad. We will build a sliding window the same size of TSA. If the size of TSA is M, then the sliding window will start at index I and end at index I plus M. Start sliding the window across the haystack. Is that fit the needle TSA? DBU, is that fit the TSA? BUT, does it fit TSA? UTS, is that the same as TSA? TSA, this substring match. We will return the index I. Awesome. Now you got the idea. If everything makes sense so far, now let's translate this logic into Python. First, define N and M as the length of the haystack and needle. Start sliding the window through the haystack for I in range 0 to N minus M. If the sliding window match the needle, return the position I. If we finish the loop without finding a match, return -1. That's it. Slick, efficient, and zero first. Time to mash the submit button. Accept it. That's a fast solution with no extra space, just a loop and string slicing. That's it for today. If this walkthrough helped you out, I'd love to hear you stick around. Please subscribe, hit the like button. Hi everyone, I'm Alan, and this is Leetcode Simplified, where we walk through Leetcode problems the easy way. Today, we're tackling Leetcode 35, search insert position. It's a classic binary search problem, and once you understand it, you see how elegant and efficient it really is. The task is simple. Given a sorted array of distinct integer and a target value, return the index of the target if it's in the list. If it is not in the list, return the index where it would be if inserted in order. Let's use binary search because it's perfect for already sorted lists. Start with the left pointer at index 0 and the right pointer at the very last index. Now we enter a loop that keeps going as long as left smaller or equal to right. Inside the loop, find the middle index. If the middle element equals the target, great. We just find the target. Return the middle index immediately. If the target is smaller than the middle element, move the right pointer to the left of the middle because we need to search the left side of the middle. If the target is larger than the middle element, move the left pointer to the right because we need to search the right side of the middle. If the target is not in the list, the while loop will finally come to an end. The left pointer now will be where the target would be if inserted. Now we step through this algorithm using the below example. Watch carefully. This is where the logic becomes crystal clear. Define the left pointer, point to the very first element, and the right pointer, point to the last element of the list. As long as the left is not greater than right, do the following. Calculate the middle index right here. Compare it with target 5. 5 is greater than 3. Then move the left pointer to the right side of the middle pointer. Left is still smaller than right. Then recalculate the middle pointer. At this time, it will point to 5. And now compare 5 with target 5. We found it, we return the index of 5 within the middle. 0, 1, 2. We return 2. Moving on to the next example, we need to find 2 inside the array. First, set up the left and right pointer which point to the first and last element. Now enter a loop as long as left is smaller or equal to right. Find the middle element here. Compare 3 with target 2. 2 is smaller. Then we need to move right pointer to the left of the middle because we need to search the left side. Left is not greater than right. Continue the loop. Recalculate the midpoint 1 and compare middle element 1 with target 2. 2 is on the right side of 1. Then we need to move left pointer to the right side of the middle 3. At this time, left pointer is greater than the right pointer. The loop terminated. The position of target 2, if it would be inserted into the array, is at the left index 0, 1, return 1, where is number 2 would be inserted in order. Example 3, find target 7 inside the array, or if not there, then find the position where it should be. First thing first, set up the left and right pointer which point to the first and last elements. As long as left has not surpassed right, find the middle pointer and compare 7 with 3, the middle element. So 7 is on the right of 3. Move the left pointer to the right of 3. Left not surpassed right, find the middle element. Compare 7 with the middle element 5. 7 is on the right of 5. Then advance left pointer to the right of the middle element. Left still has not surpassed right. Continue. Middle pointer also point to 6. Compare 7 with 6. 7 on the right of 6. Move the left pointer to the right of 6. At this time, the left pointer surpassed the right pointer. The loop terminates. Return the left pointer. Position 4. 0, 1, 2, 3. So position 4 is the index or the position where target 7 would be if inserted in the array in order. Alright, let's translate this logic into Python. First of all, set the left and the right pointer point to the first and the last elements. So now we enter the while loop. As long as the left index has not surpassed the right index, do the following. Find the middle position. Integer divide. So in Python, integer division means we divide and we float it down to the nearest integer. For example, 5 integer divide 2 is 2. Instead of regular division, 5 divide 2 is 2.5. 7 integer divide 2 is 3, not 3.5, not a regular division. Alright, keep moving. So we got middle position. Compare if target is the same as the middle elements, then we found the target inside the array. Return its position. Else, if the target is smaller than the middle elements, move right pointer to the left of the middle pointer. Else, the last case, do the opposite. Move left to the right of the middle element. If the target is not in the array, the loop at some point will terminate. Left will be the position where the target would be if inserted. Return left index or left pointer. Alright, and we're done. Was clean, fast, and to the point. A textbook binary search. Let's hit that submit button. Boom, one shot, accepted. If that helped you cross this problem, drop a like and subscribe for more walkthroughs like this. Catch you in the next one. Thanks for watching. Hello everyone, I'm Alan and this is Leetcode Simplified, where we walk through Leetcode problems the easy way. Today we're tackling Leetcode 58, length of the last word. This problem, short and sweet. The task is simple. Given a string as considered word and space, which may include leading and trailing space, return the length of the last word. For example, the last word in this string is word and this length is 5. The length of moon, last word in this string is 4. The steps are simple. First, remove leading and trailing spaces from the string. Second, break the string into a list of words. Third, get the last word. Finally, get its length. Look at the second example below. Given the string fly me to the moon, step 1, remove trailing space. It becomes fly me to the moon. Next, break this string to a list of words. Fly me to the moon. Third, get the last word in the list, which is moon. Lastly, calculate its length, which is 4. Return 4. Translate these steps to Python. String S, strip all the trailing spaces. Next, split into a list of words. Retrieve the last word in the list. Now get the length of this word using function length. Let's practice writing this one more time. Strip all the trailing spaces, then split it into a list of words. Then retrieve the last word in the list and get its length. That is the result. No need for loops, just a clean one-liner, short and sweet. Done. That was fast, clean, and straight to the point, the Pythonic way. Hit the submit button. Boom, one shot, accepted. If that helped you simplify this problem, drop a like and subscribe. Hello everyone, I'm Alan and this is Leetcode Simplified, where we walk through Leetcode problems the easy way. Today, we're tackling Leetcode 66 plus 1. Given an array of digits represent a positive integer, add 1 to it and modify in place and return the resulting array. Everyone knows how to add 1 to a number on paper. Sounds simple, right? Well, it is, mostly, but we need to handle carryovers correctly, especially when we have trailing lines. Take a look at the below example and let's animate this logic step by step. Just like we do addition by hand, go through the digits from right to left, add 1 to 3, so 4. When we go through digits from right to left, if it's less than or equal to 8, add 1 and return the resulting array. If the digit is 9, change it to 0. Repeat the process. Go to next digit 2, add 1 because it's a carry on. Add 1 to 2 is 3 and return. Done. So the given array is 1, 2, 9. The resulting array will be 1, 3, 0. How about this time it is 1, 9, 9 instead. Again, go through digits from right to left. If it's 9, change it to 0 and go to the next, which is also a 9. Change it to 0 and go to the next, add 1, 2 and immediately return. So after add 1 to the array 1, 9, 9, the resulting array will be 2, 0, 0. Take a look at the last case, which is a special case where all digits are 9. So given the array 9, 9, 9, add 1, go through the digits from right to left. This is a 9, change it to 0 and go on to next left, which is also a 9, change it to 0. Go to the next left, which is also a 9, change it to 0. And the loop is now ended because no more digit. The for loop exit, add the carryover 1 in front. The initial given array is 9, 9, 9 and after adding 1 we modify it and return the resulting array as 1, 0, 0, 0. Alright, let's code it up. For every position in the reverse orders of the array in full range, if anytime the digits is less than or equal to A, you just add 1 to it and return the resulting array. If the digit is 9, set it to 0 and move on to the next left. If we exit the loop, that means all the digits were 9, so we return 1 in front, the resulting digits. Basically, we just return a new array starting with digit 1 followed by all zeros. And we're done. That was clean, logical, and straight to the point. We handle the case where all the digits are 9. Let's mark that submit button. Boom. Accepted. One shot. If that helps simplify the logic for you, drop a like and subscribe for more clear and beginner-friendly walkthroughs.
Hello everyone, I'm Alan and welcome back to Leetcode Simplified, where we solve problems the easy way. Today we're tackling Leetcode 67, add binary. Given two binary strings, return their sum, also as a binary string. First things first, we need to understand how binary addition works by hand. Let's add 1100 and 1110 and observe what happens, column by column. First column, 0 plus 0 equals 0. That's even, so the binary digit here is 0. Next column, 0 plus 1 equals 1. Odd, so we write 1. Next, 1 plus 1 equals 2. Even, we write 0 and carry over 1. Last column, 1 plus 1 plus 1 equals 3. Odd, we write 1 and carry 1 again. Finally, that carry 1 gets written in front, so the result is 1, 1, 0, 1, 0. From this, we can observe two important mental shortcuts. If the total is even, the binary digit is 0. If the total is odd, the binary digit is 1. That's what total modulo 2 tells us. It checks for even or odd. If the total is 2 or 3, we carry over 1 to the next column. That's exactly what total floor divided by 2 does. It gives us the carry. Now let's turn that logic into Python. We start with an empty list to store the result. Set pointers I and j to the end of each binary string. Initialize carry as 0. Then we loop as long as either string still has digits left or there's a carry. At each step, start with the carry as the total. If it has a digit, add it as an integer to the total and move I left. Same for B. Add digit to total and move j left. The current binary digit, total modulo 2, convert it to a string and append it to the result. Update the carry as total floor divided by 2. Finally, reverse the result list and join it into a string. That's your answer. Let's go ahead and hit the submit button. Whoops, there is a typo. Here it is. Let's resubmit. Great, accepted. And that's it. No built-in conversions, no binary headaches, just basic math, a clean loop, and one simple mental trick. Even total, write 0. Odd total, write 1. Carry over if total is 2 or 3. If this helped, drop a like and subscribe for more beginner-friendly LeetCode walkthroughs. I'm Alan, this is LeetCode Simplified. See you in the next one.
Hello everyone, I'm Alan. Welcome to Leetcode Simplified, where we solve problems the easy way. Today, we're tackling Leetcode 69, square root of x. Given a non-negative integer x, find the square root of x. Round it down the integer part only of the square root. Quick example, square root of 8 is about 2.8. But the problem only wants to return the integer part. 2. In mathematical terms, it means given x, find the largest integer m such that m times m less than or equal to x. Here is our approach. Use binary search. Because binary search is optimized for finding breakpoint in monotonic range. Exactly fit this problem. Our binary search do not apply to these two special cases, so we handle them here. If x is 0, its square root is 0. If x is 1, its square root is 1. Here is our main focus, binary search. For any x larger than 1, square root of x cannot be larger than half of x. In the range between 1 and half of x, find the middle and compare middle times middle to x. If equals, middle is the square root. If middle times middle less than x, then the square root must be larger than that middle. So move the left boundary to middle plus 1. If middle times middle greater than x, then the square root must be smaller than that middle. So move right boundary to middle minus 1. Repeat the process again and again until left boundary and right boundary cross each other. Then stop and return the right boundary because left boundary had just gone beyond the correct answer, the threshold, and the right boundary is the largest possible number where right times right is still smaller than x. We want only the integer part of the square root. Let's do a walkthrough with the following two examples below to understand this better before we implement it in Python. We're looking for the square root of 4. Now, intuitive says the square root of x cannot be larger than half of x. Try half of 4, which is 2. 2 times 2 equals 4. Then 2 is the square root of 4. That's simple enough. Next example. Find square root of 8. The square root of 8 cannot larger than half of 8, 4. So we will perform a binary search from 1 to 4. Initially, the left boundary is 1, right boundary 4. The middle is 2, and 2 times 2 less than 8, so the square root must be larger than 2. Set left boundary to 3. Middle is now 3. 3 times 3 greater than 8. Square root must be smaller than 3. Set the right boundary to 2. The right boundary is now smaller than the left boundary. A second ago, we already knew that the left was not a good choice, but the right is, because the right times right is still less than 8. So return the right boundary. Let's turn that into Python. First of all, if x smaller than 1, return x. Because the square root of 0 is 0 and square root of 1 is 1. Set the boundary for our binary search from 1 up to half of x. And as long as the left boundary and the right boundary has not crossed each other, do the following. Find the middle and compare middle times middle to x. If equals to x, that middle is the perfect square root of x. If middle times middle less than x, then that middle is not a good candidate. Must be on the right of the left boundary, and we move the left boundary to the current middle plus 1. Similarly, if greater than x, then that middle is not a good candidate. The correct square root must be on the left of the right boundary. So move the right boundary to middle minus 1. Repeat above operations as long as left boundary and right boundary do not cross each other. If they do, terminate the while loop and return the right boundary because we just knew that left boundary was not a good choice. Right boundary is still because right times right is still less than x. So we return the right boundary. Okay, done. That's all to it. Let's smart that submit button. Boom, accepted. A clean, efficient binary search that gives the integer part of the square root fast and accurate. No need for guessing, no floating point math, just simple logic the easy way. If this helped, drop a like and subscribe for more beginner-friendly Leetcode walkthroughs. I'm Alan and this is Leetcode Simplified. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're solving Leetcode 367, valid perfect square. Given a positive integer x, return true if x is a perfect square of some integer m. In other words, if you can find an integer m such that m times m equal x, return true. By the way, m is called the perfect square root of x. Here is our approach. We will use a binary search because it is optimized for finding breakpoints in monotonic range. In the case we are searching for breakpoint m, such that m times m equals a given x in a sorted dataset 1, 2, 3, and so on. That's perfect for binary search. But first, let's take care of this special case. 1 is a perfect square because 1 equals 1 times 1. Now, here is our main focus, binary search. For any x larger than 1, perfect square root cannot be larger than half of x. So initially, we search in the range between 2 and half of x. Calculate the middle of that range and compare middle times middle to x. If equals, then middle is m, the perfect square root. Return true. If middle times middle less than x, we want to search the perfect square root on the right side of the middle. How to do that? Move left boundary to middle plus 1. Likewise, if middle times middle is greater than x, search the perfect square root on left side. And how to achieve that? Set right boundary to middle minus 1. Repeat these steps until we find the perfect square root, or left boundary and right boundary cross each other. Then stop the process and return false. No perfect square root for that given x. Let's animate below example step by step. We're looking for the perfect square root of 16, if any. Our intuitive says the perfect square root of x cannot be larger than half of x, 16, which is 8. So we start the binary search from 2 to 8. Initially set left boundary at 2 and right boundary at 8. The middle is 5, and 5 times 5, 25 is greater than 16x. So the perfect square root, if any, must be smaller than 5. So we move the right boundary to 4 so that we can search the left side of the middle 5. In the new search range from 2 to 4, the new middle is now 3, and 3 times 3, 9, is less than 16. So the perfect square root, if any, will be larger than 3. To search the right side of 3, we move the left boundary to 4. In the new search range, both left and right point to 4. Then the new middle also point to 4. 4 times 4 equals 16. It means 4 is the perfect square root. 16 is perfect square. Return true. Now that we understand the logic, let's implement it in Python. First, if x equals 1, return true. 1 is a perfect square. Initially, set the search range from 2 to half of x. As long as left boundary not cross right boundary, do the following. Find the middle and compare middle times middle to x. If equal to x, return true. X is a perfect square. If middle times middle is less than x, search right side of middle. So move left boundary to middle plus 1. And finally, if middle times middle greater than x, search left side of middle. Set right boundary to middle minus 1. If left and right boundaries cross each other, the while loop will exit return false because there's no perfect square root. And that's how you check if a number is a perfect square, fast and clean. Let's hit the submit button. Boom, accepted. Binary search gives us the answer with no need for square roots or floating point math. Just smart logic and integer precision. If this makes sense, give it a like and subscribe for more simplified Leetcode guys. I'm Alan and this is Leetcode Simplified. Catch you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're solving Leetcode 70 clamping stair. How many distinct ways to reach level N if you take 1 or 2 steps at a time? Let me construct this beautiful staircase and we get down to business. This is the ground, level 1, level 2, level 3, and so on and so forth. Now, let's say you are standing at level 20. How many distinct ways could I possibly taken to get here, you ask? Well, You just climb up from level 19 or 18. Then just add the total number of ways for you to reach level 19 and 18. There are 6,765 ways to reach level 19, 4,181 ways to reach level 18. 10,946 is the number of ways for you to reach level 20. That's it. At any level n, the number of ways to reach there equals the number of ways to reach level n-1 and the number of ways to reach level n-2. Just add the previous two to find the next one. Sound familiar? Yes, this is just the Fibonacci sequence in disguise. How about the number of ways to 17, 16, 15, you may ask? We can find the answer by starting from this. 1 way to reach level 1, 2 ways to reach level 2, 1 step, or single 2 step. Given the two base cases, we can find the number of ways to reach any level. 3 ways to reach level 3, 5 ways to reach level 4, 8 ways to reach level 5, and so on. Let's translate this logic into Python. Use interactive approach, no recursion, no memorization, no extra space. Just the best and most optimal solution. We already knew there is 1 way to reach level 1, 2 ways to reach level 2. Set variable A, number of ways to reach level 1. B, number of ways to reach level 2. At each level from level 3 to level n. Set the new A equals to the old B. The new B is the sum of the previous A and B. After the loop, the final B will hold the number of ways to reach level n. Let's hit the submit button. Boom! Accepted. This iterative logic is efficient. Time complexity is O(n), 1 pass. Space complexity is O1. Just 2 variables. No recursion, no stack overflow. Just clean math based on how stairs can be climbed. And that's how you solve climbing stairs. Fast, simple, and clean. Fibonacci in disguise, implemented with a few lines of code. If this helps simplify the problem for you, give it a like and subscribe for more logical Leetcode guides. I'm Alan and this is Leetcode Simplified. Hello everyone and welcome back to Leetcode Simplified. I'm Alan and today we're solving Leetcode 83. Given pointer head to a sorted linked list, remove duplicates in place so that each value appears only once. The modified linked list should remain sorted as well. Because the linked list is sorted, duplicates are next to each other. Just simply reroute the next pointer appropriately. The process will be much simpler than you might thought. Let's walk through 2 examples below step by step to see how we can manipulate pointer to skip duplicate nodes. First, create pointer curve to point to the same node 1 as pointer head. We use curve to traverse the linked list and manipulate pointers appropriately. Curve points to a node of value 1. Curve next points to a node also of value 1. We want to skip the second one by pointing curve next to curve next. Curve now point to 1 and curve next point to 2. Values are different. Simply advance curve to curve next. Curve is now 2 and curve next is none. That's the end of the linked list. So we return pointer head, which points to the first node of the modified linked list 1 to 2. Next example, given pointer head that points to the first node of the linked list 1 to 1 to 2 to 3 to 3. First, create pointer curve to also point to where the pointer head points to. Compare values of the 2 nodes that curve and curve next point to. Curve points to the node of value 1. Curve next points to the node also of value 1. We want to skip the second one by pointing the curve next to curve next. Compare again. Curve points to node of value 1 and curve next points to a node of value 2. values are different. Advance curve to curve next. Repeat the comparison. Curve now point to a node of value 2. Curve next point to a node of value 3. Different. Simply advance curve to curve next. Compare again. Curve now point to a node of value 3. Curve next point to another node also of value 3. Skip the second 3 by point curve next to curve next. Now curve next is none. It means the node curve points to is the last node. Return the pointer head with points to 1 to 2 to 3. If we clear all the steps, it's time to implement them with Python. First thing first, create pointer curve to point to the same node as pointer head. We use curve to walk through the list. As long as curve and curve next are not none, compare their values. If they're equal, point curve next to curve next to skip the duplicate. If different, advance curve to the next node. If curve is none because the linked list is empty, or if curve next is none, no more node, exit the while loop and return pointer head with points to the first node of the modified linked list. Alright, let's mark the submit button. Boom, accepted. Just some clean, simple and efficient pointer manipulation in a linked list. Time complexity linear (ON) because each node is visited only once. Space complexity constant O1 because the process is done entirely in place. If this breakdown makes it clear for you, drop a like and subscribe for more simplified Leetcode tutorials. I'm Alan and this is Leetcode Simplified. Catch you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're tackling Leetcode 88, Merge Sorted Array. We need to fully understand the problem setup first. Given two sorted arrays, nums1 with m is the number of its valid element and nums2 with n is the number of its elements. And the problem automatically adds n zeros to the end of nums1 as placeholders. The total length of nums1 is m plus n. Our task is to merge nums2 into nums1 in place so that the final versions of nums1 is still sorted. Here's how we're going to do it. Since nums1 has a bunch of trailing zeros, we can safely override nums1 from the end with the biggest elements from either array. Let's animate this approach with the three examples below. Example 1. Num1 has 3 valid elements. Nums2 have 3 valid elements. Therefore, n zeros are added to the end of nums1. Given all that, here what we'll do. Set I points to 3, the last valid element in nums1. J points to 6, the last element in nums2. K points to 0, the last element in nums1. Start the iteration process. At K position, place the bigger of 3 and 6 and move J left from 6 to 5. Then move K left. Repeat the process. At the new K position, place the bigger of elements at I and J. 5 is bigger than 3. Move J left from 5 to 2. Then move K left. Repeat the process. At the new K position, place the bigger of elements at I and J. 3 is bigger than 2. Move I left from 3 to 2. Then move K left. Repeat the process. At the new K position, place the bigger of elements at I and J. They are both 2, so place the 2 from J to K. And move J left, then move K left. At this time, J points to -1, indicating that nums2 runs out, so we stop the process. That's it. Nums2 has been merged into nums1. Move on to example 2. I point to 1, the last valid element in nums1. J points to -1 because nums2 is empty. K also points to 1, the last element in nums1. The iteration process won't start because nums2 is empty. And voila, that's it. Nums1 is the result of merging itself with another empty array. Finally, example 3. I points to -1 because nums1 has no valid element. J points to 1, the last element in nums2. K points to 0, the last element in nums1. Since nums1 has no valid element, just copy elements from nums2 into the placeholders in nums1. Copy 1 from nums2 to the K position in nums1. Alright, if we're clear on the logic, let's translate that into Python. Start by setting 3 pointers. I points to the end of the valid portion of nums1. J points to the end of nums2. K points to the very end of nums1. This is where we'll place the next biggest element. Now, loop from both position I and J as long as they are greater than 0. If nums2 element is bigger, override nums1k with it and move J left 1 position. Else, if nums1 element is bigger, override nums1k with it and move I leftward 1 position. After nums1k get overwritten, move k left 1 position to get ready for the next largest element. Now, here's the special case. Nums1 runs out of elements, but nums2 still have some left. Just copy them into nums1. Why don't we do the same for nums1? Well, if nums1 has leftovers, they're already in place in sorted order. No need to touch them. It's time to smash the submit button. Boom! Accepted. Great. This solution runs in O m+n time and does everything in place using just constant extra space. Simple, efficient, and easy to understand once you visualize the pointers working from the end. And that's how you merge two sorted arrays in place. If the explanation helped you, give it a like and don't forget to subscribe for more simplified Leetcode tutorials like this. I'm Alan and this is Leetcode Simplified. Thanks for watching. I'll see you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're going to walk through Leetcode 94 binary tree in order traversal. Given the root of a binary tree, return an array of all nodes value in order sequence. We will use an iterative approach to learn the logic step by step, simulate the system called stack that recursion would normally use. Let's first quickly revisit what in-order traversal means. In binary trees, in-order means we visit nodes in left, root, right order. Here's my two-phase process. Phase 1. Use pointer curve to go left as far as possible and append nodes along the way onto the stack. Phase 2. When you add a node with no left child, pop the stack and go to the pop node. Add its value to the result array, then go right. Repeat the two-phase process until no more nodes or stack is empty. Let's walk through example 1 step by step. Given pointer root that points to node value 1 of binary tree 1, node 2, 3. First of all, create pointer curve to point to the same node as root. Curve will be used to traverse the whole tree in order. Let's begin the two-phase process. Phase 1. Curve goes left as far as possible while appending nodes along the way to a stack. Append to the stack node value 1 before move curve left. Curve now points to none, means no more node. Then phase 2. Pop the stack and points curve to the pop node value 1. Write its value 1 to the result array and move curve right. Repeat the two-phase process. Phase 1. append to the stack node value 2 before move curve left. Append node value 3 to the stack before move curve left again. Curve now points to none, so begin phase 2. Pop the stack and points curve to the pop node 3. Write value 3 to the result and move curve right. Repeat the process. Curve is none. There is no left sub 3 to go, so skip phase 1. Phase 2. Pop the stack and points curve to the pop node 2. Write value 2 to the result and move curve right. Now curve is none and the stack is empty. We end the entire process. Return the result array which contains all the nodes value in order traversal. Let's move on to the second example. Given pointer root that points to the node value 1 of binary tree. 1, 2, 3, 4, 5, no, 8, no, 6, 7, 9. First of all, create pointer curve to point to the same node as root. Curve is used to traverse the whole tree in order. Begin the two-phase process. Phase 1. Curve goes left as far as possible while appending nodes along the way to the stack. Append to the stack node value 1 before curve goes left. Append node value 2 to the stack before curve goes left. Append node value 4 to the stack before curve goes left again. Curve is none, no more left to go. Begin phase 2. Pop the stack and points curve to the pop node 4. Write value 4 to the result and move curve right. Repeat the process. Curve is none, no left. Skip phase 1. Phase 2. Pop the stack and points curve to the pop node 2. Write value 2 to the result and move curve right. Repeat the two-phase process. Phase 1. Append node value 5 to the stack before curve goes left. Append node value 6 to the stack before curve goes left. Curve is none now, no more left. Phase 2. Pop the stack and points curve to the pop node 6. Write value 6 to the result and move curve right. Curve is none, no left, so skip phase 1. Phase 2. Pop the stack and points curve to the pop node 5. Write value 5 to the result and move curve right. Repeat the two-phase process. Phase 1. Append node value 7 to the stack before move curve left. Curve is none, no more left. Phase 2. Pop the stack, points curve to node 7. Write value 7 to the result and move curve right. Curve is none, no left, so skip phase 1. Phase 2. Pop the stack and points curve to the pop node 1. Write value 1 to the result and move curve right. Repeat the two-phase process. Phase 1. Append node value 3 to the stack before move curve left. Curve is none, no left, so skip phase 1. Phase 2. Pop the stack and points curve to the pop node 3. Write value 3 to the result and move curve right. Repeat the two-phase process. Phase 1. Append node value 8 to the stack before move curve left. Append node value 9 to the stack before move curve left. Curve is none, no more left. Phase 2. Pop the stack and points curve to the pop node 9. Write value 9 to the result and move curve right. Curve is none, no left, so skip phase 1. Phase 2. Pop the stack, point curve to the pop node 8. Write value 8 to the result and move curve right. Finally, curve points to none and the stack is empty. We end the two-phase process. Return the result array which contains all the nodes value in order traversal. Alright, are you still with me? Let's jump right into Python. First of all, create an empty stack and an empty result array. Next, create pointer curve to point to the same node as root. Now, begin the two-phase process that will run as long as curve is not none or the stack is not empty. In phase 1, keep moving curve left as far as possible. Append the node to the stack along the way. Phase 2 begins when we add a node with no left subtree. Then pop the stack and point curve to that pop node. Append the pop node value to the result array and move curve right. Finally, when curve is none and the stack is empty, end the two-phase process. Return the result array, which contains all the nodes values in Inorder Traversal. That's it. It's time. Let's mark the submit button. Boom, accepted. This solution runs in O(n) time, where n is the number of nodes, and use OH space, where h is the height of the tree due to the stack. It's a clean, reliable method and avoids the recursion limit for large trees. Understanding how to simulate recursion with a stack is a powerful skill in tree problems. If you can walk the control flow like we just did, you'll be in great shape for many more tree questions. Hope this makes sense and help clarify how interactive Inorder Traversal works. If it did, give it a like, drop a comment with questions, and don't forget to subscribe for more step-by-step Leetcode walkthroughs. I'm Alan and this is Leetcode Simplified. Thanks for watching, and I'll see you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're going to walk through Leetcode 144, binary tree preorder traversal. Given the root of a binary tree, return an array of all node values in preorder sequence, root left right. We are going to solve this iteratively, not recursively, and simulate the core stack manually using a stack. This way, we avoid hitting recursion limits on large trees and fully understand what's going on under the hood. Here is my two-phase process. Phase 1. Pop the stack. Point curve to the pop node, then append its value to the result array. Phase 2. Append right child, then append left child onto the stack. Repeat this two-phase process until the stack is empty. Let's animate example 1 step by step. Given pointer root that points to node value 1 of a binary tree, 1, node, 2, 3. First thing first, append the root node value 1 onto the stack. Now begin the two-phase process. Phase 1. Pop the stack. Create pointer curve to point to the pop node 1. Then append value 1 to the result array. Phase 2. Append right child node value 2 to the stack. No left child. Repeat the process. Phase 1. Pop the stack. Points curve to the pop node 2. Then append value 2 to the result. Phase 2. Node value 2 has no right child. Append left child node value 3 to the stack. Repeat the process. Phase 1. Pop the stack. Points curve to the pop node 3. Then append value 3 to the result. Phase 2 won't happen because node 3 has no children. The stack is now empty. Terminate the process and return the result array that has all the node values in the preorder sequence. Move on to the second example. Given pointer root that points to the node value 1 of a binary tree, 1, 2, 3, 4, 5, no, 8, no, 6, 7, and 9. First thing first, append the root node value 1 onto the stack. Begin the two-phase process. Phase 1. Pop the stack. Create pointer curve to point to the pop node 1 and append value 1 to the result. Phase 2. Append right child node value 3 and left child node value 2 onto the stack. Repeat the process. Phase 1. Pop the stack. Point curve to the pub node 2 and append value 2 to the result array. Phase 2. Append right child node value 5 and left child node value 4 onto the stack. Repeat the process. Phase 1. Pop the stack. Point curve to the pub node 4 and append value 4 to the result. Skip phase 2 because node value 4 has no children. Repeat the process. Phase 1. Pop the stack. Point curve to the pub node 5 and append value 5 to the result. Phase 2. Append right child node value 7 and left child node value 6 onto the stack. Repeat the process. Phase 1. Pop the stack. Point curve to the pub node 6 and append value 6 to the result. Skip phase 2 because node value 6 has no children. Repeat the process. Phase 1. Pop the stack. Point curve to the pub node 7 and append value 7 to the result. Skip phase 2 because node value 7 has no children. Repeat the process. Phase 1. Pop the stack. Point curve to the pub node 3, then append value 3 to the result. Phase 2. Append right child node value 8 to the stack. No left child. Repeat the process. Phase 1. Pop the stack. Point curve to the pub node 8, then append value 8 to the result. Phase 2. Node value 8 has no right child. Append left child node value 9 to the stack. Repeat the process. Phase 1. Pop the stack. Visit the pub node 9 and append value 9 to the result array. Skip phase 2 because node value 9 has no children. The stack is now empty, so terminate the process and return the result array that has all the node values in preorder traversal. Alright, if we clear on the process, let's jump right into Python. If no root, no tree, return empty array. First thing first, append the root onto the stack. Create empty array result to hold node values. Now begin the two-phase process and repeat as long as the stack is not empty. Phase 1 begins by popping the stack and point curve to the pub node. Then append its value onto the result array. In phase 2, append the right child, then the left child, if any. This process continues until the stack is empty. Then exit the process and return the array result that has all the node values in preorder sequence. Done. Let's mark the submit button. Boom, accepted. That's it. This solution runs in ON time, where N is the number of nodes, and use OH space, where H is the height of the tree due to the stack. This method is clean, recursion free, and handles large trees without hitting stack limits. Understanding how to simulate recursion with a stack is a powerful skill in tree problems. If you're able to walk through this stack-based simulation step by step, you're building a foundation for tackling many more tree problems with confidence. If this helped, give it a like, leave a comment with any questions, and subscribe for more step-by-step Leetcode walkthroughs. I'm Alan and this is Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan. Today we're going to walk through Leetcode 145, binary tree postorder traversal. Given the root of a binary tree, return an array of all node values in postorder sequence left, right, root. We will solve this iteratively by simulating recursions using a stack. This helps avoid recursion limits on large trees and most importantly understand what's happening under the hood. Here is the trick. At first, traverse the whole tree in root, right, left order. Then at the end, we reverse the result to left, right, root with the postorder we want. Here is my two-phase process. Phase 1. Pop the stack, point curve to the pub node, then append its value to the result array. Phase 2. If they exist, append left child first, then right child onto the stack. Repeat until the stack is empty. At the end, reverse the result array to get postorder. Let's animate example 1 step by step. Given pointer root that points to node value 1 of a binary tree, 1, node, 2, 3. First thing first, append the root node value 1 onto the stack. Now begin the two-phase process. Phase 1. Pop the stack. Create pointer curve to point to the pop node 1. Then append value 1 to the result array. Phase 2. Node 1 has no left child. Append right child node value 2 onto the stack. Repeat the process. Phase 1. Pop the stack. Points curve to the pop node 2. Then append value 2 to the result. Phase 2. Append left child node value 3 onto the stack. No right child. Repeat the process. Phase 1. Pop the stack. Points curve to the pop node 3. Then append value 3 to the result. Phase 2 won't happen because node value 3 has no children. The stack is empty. No node to pop. Return array result. Reversed. All node values will be in postorder. Let's move on to the second example. Given pointer root that points to node value 1 of binary tree, 1, 2, 3, 4, 5, no, 8, no, 6, 7, and 9. First thing first, append the root node value 1 onto the stack. Now begin the two-phase process. Phase 1. Pop the stack. Create pointer curve to point to the pop node 1 and append value 1 to the result. Phase 2. Append left child node value 2 and right child node value 3 onto the stack. Repeat the process. Phase 1. Pop the stack. Point curve to the pop node 3 and append value 3 to the result. Phase 2. Node 3 has no left child. Append right child node value 8 onto the stack. Repeat the process. Phase 1. Pop the stack. Point curve to the pop node 8 and append value 8 to the result. Phase 2. Append left child node value 9 onto the stack. No right child. Repeat the process. Phase 1. Pop the stack. Point curve to the pop node 9 and append value 9 to the result. Skip phase 2 because node value 9 has no children. Repeat the process. Phase 1. Pop the stack. Point curve to the pop node 2 and append value 2 to the result. Phase 2. Append left child node value 4 and right child node value 5 onto the stack. Repeat the process. Phase 1. Pop the stack. Point curve to the pop node 5 and append value 5 to the result. Phase 2. Append left child node value 6 and right child node value 7 onto the stack. Repeat the process. Phase 1. Pop the stack. Point curve to the pop node 7, then append value 7 to the result. Skip phase 2 because node value 7 has no children. Repeat the process. Phase 1. Pop the stack. Point curve to the pop node 6, then append value 6 to the result. Skip phase 2 because node value 6 has no children. Repeat the process. Phase 1. Pop the stack. Visit the pop node 4, then append value 4 to the result array. Skip phase 2 because node value 4 has no children. The stack is empty, so terminate the process. Right now, the result array contains values in root right left order. We will reverse the elements of the result from root right left to left right root post order, the order we want. Alright, to make this happen, let's jump right into Python. If no given root means no tree, no nodes, return empty array. Append the root node onto the stack and create empty arrays result to hold node values. Begin the two-phase process until the stack is empty. In phase 1, pop the stack, then point curve to the pop node and append its value to the result. In phase 2, if left child exists, append it onto the stack. If right child exists, append it onto the stack. If the stack is empty, terminate the process. At this time, elements in the result array are in root right left. Reverse them to left right root. Here's easy tip to remember. Make 2 tweaks to the preorder algorithm to get this postorder algorithm. Tweak 1. Append the left child first. This gives a root right left order. Tweak 2. Reverse root right left order to left right root postorder, the order that we want. Oh, typo. Okay, we're supposed to append the root and left. Looks good. All the logic, all the coding, it all comes down to this. And now the moment we've been waiting for. Let's smart the submit button. Boom, accepted. That's it. This solution runs in ON time, where N is the number of nodes, and use OH space, where H is the height of the tree due to the stack. This method is clean, recursion free, and handle large trees without hitting stack limits. Understanding how to simulate recursion with a stack is a powerful skill in tree problems. If you're able to walk through this simulation step by step, you're building the foundation for tackling many more tree problems with confidence. If it helps, give it a like, leave a comment with any questions, and subscribe for more step-by-step Leetcode walkthroughs. I'm Alan and this is Leetcode Simplified. Thanks for watching. I'll see you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan, and in today's video we're solving Leetcode 94 binary tree Inorder traversal. Given the root of a binary tree, return a list of all node values in Inorder traversal. That is left subtree, root, right subtree. We're going to use recursion. The function will keep calling itself until it reaches the bottom of the tree, and then it will start returning results upwards. This means when the root is none, return an empty list. Otherwise, get the Inorder result from the left child, then add the current node's value, then get the Inorder result from the right child. Finally, combine and return the result. The coding is quite easy. Let me show you how. If the root is none, return an empty list. Otherwise, return the result from the left subtree, then concatenate with the root value. Then concatenate it with the results of the right subtree. And that's it. This one line elegantly captures the full Inorder traversal logic. Let's take a closer look at the example below. Given the pointer root that points to the node value 1. Let's break it down step by step. We call the function with the given root node value 1, f1. The function will call itself with the left child of node value 1 plus node 1's value itself, plus the function will call itself with the right child of node value 1. Like above, f of 2 will call itself on the left child of node value 2, which is f4, plus the value of node value 2 itself, plus f of 5. f of 3 produce value 3 and f of 8. Node 4 doesn't have a left subtree and right subtree, so it's only return value 4. f of 5 return the left subtree f of 6 plus the value 5 itself plus f of 7, the right subtree. Likewise, f of 8 return f of 9, the value 8 itself. f of 6 and f of 7 return value 6 and value 7 because node value 6 and node value 7 do not have left or right subtree. Node value 9 has no left or right subtree, So f of 9 return value 9 only. Let's display all the values in one row. Now concatenate all the lists into one list. And that is all the node values in Inorder Traversal. This elegant one-line recursive solution is so clean compared to the iterative version. Get the entire traversal logic in one readable statement. Alright, time to smash the submit button. Moment of truth. Boom, accepted. Time complexity is O(n). We visit every node once. Space complexity is O(n) in the worst case due to the core stack. And that's how you solve binary tree in Inorder Traversal recursively. We follow the classic left root right pattern, and Python list concatenate made it incredibly clean. Since the recursive approach is so elegant, and Preorder and Postorder traversals follow very similar logic, let me show you the full code to those as well. Move it out of the way. Create a function for Preorder and another function for Postorder. Change this to Preorder. Change this to Postorder. In Preorder, we return the root value first, and in the Postorder traversal, the root value will be returned last. And that's all I've got for today's video. All three binary tree traversals solved using the recursive approach: Inorder, Preorder, and Postorder. Each just a few elegant lines of Python. If this helped you, please like, comment, and subscribe to Leetcode Simplified for more clear, beginner-friendly tutorials. I'm Alan. Thanks so much for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan, and today we're walking through Leetcode 100 same tree. Given two binary trees, check if they are the same. That means they have the same structure and corresponding nodes have the same value. We will use recursion approach, recursively traverse down each subtree at the same time and compare its pairs of nodes. There are three possible cases that can happen. Case 1. If both nodes are none, that means we reach the end of this branch and everything matched so far return true. Case 2. If two corresponding nodes are not structurally identical, that means one node exists but the other doesn't, or both exist but their values are different. Return false. Case 3. The two corresponding nodes match. We now recursively compare their left children, and then recursively compare their right children. Return the result of both comparison. That's the full logic. Let's walk through three below examples to visually see how this works. Given binary tree with a root node value 1 and second binary tree also with root node value 1, we want to check if they are the same. Okay, so we call the function isame3 with the root nodes of both trees. This node exists, this node exists, and their values are the same. So continue, check their left children f2 and 2, and check their right children f3, 3. F2, 2, compare this node and this node, their values are the same. So continue, check their left children f none, none, and their right children also f none, none. So we are checking these two nodes. Because p and q is none, then we return true. F none, none here also return true. Similarly, F3, 3, checking these two nodes, this node and this node. Their values are the same, so we continue checking their left children and their right children. Left children are none and none, and right children also none and none. Just like before, if both nodes are none, return true for that function. So f none none return true. At this stage, no more call, so we combine final answers true. Let's take a look at the next example. First, call Isym3 on the two root nodes 1 and 1. Both node 1 have the same value. Continue proceeding, checking their left and right children. F2 none and F none 2. F2 none will check node 2 and none and return false. Because the AND operator, the whole process terminate and return false. Moving on to the last example, example 3. Like above, first call the function Isym3 on the two root nodes 1 and 1. Both nodes 1s are the same. F11 continue calling their left children, F21 and their right children, F12. F21 compare the value 2 and value 1 of the two nodes. Of course they're different, so F21 return false. And since we have the logical operator AND in our return, we have early return false. Don't need to proceed any further. We just went through 3 examples. We walked down both trees at the same time, comparing each pair of nodes. If both nodes are none, good. If one is missing or their values don't match, return false right away. Otherwise, keep checking both left and right subtrees. Alright, time to submit. Boom, accepted. So that's how the recursive Isym3 function works. Clean and elegant solution that really solve power up recursive for 3 problems. You found this helpful? Check out the other binary tree videos on the channel. I'm Alan and this is Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're walking through Leetcode 101 Symmetric Tree. Given the root of a binary tree, determine if it is symmetric around its center. In other words, the left subtree and the right subtree mirrors each other. We'll solve this using a recursive approach, very similar to the technique we use for checking if 2 binary trees are the same. But here's the tweak. A symmetric function only takes 1 tree A parameters. So, to compare the left subtree and the right subtree to check if they mirror each other, we define a helper function IsMirror that takes 2 parameters, left subtree and right subtree. We use IsMirror function to recursively work down the left and the right subtrees at the same time in opposite directions. If one goes left, the other goes right, and vice versa. At each step, compare 2 corresponding nodes, one from the left subtree, one from the right subtree. Here are the 3 possible cases when comparing 2 nodes. Case 1. If both nodes are none, that means we reach the end of both branches at the same time and everything matched so far, so we return true. Case 2. If only one node is none, or both nodes exist but their values are different, the symmetry is broken, so we return false. Case 3. If both nodes exist and values match, continue comparing their children in the opposite direction. Compare the left child of the left node with the right child of the right node, and compare the right child of the left node with the left child of the right node. Then return their combined result. So what we're doing is mirroring our path down both sides of the tree, making sure each node on the left match its corresponding mirror node on the right. And finally, there's one special case to take care of. If the input tree is empty, it's symmetric by default. Otherwise, we want to check whether the left and right subtree of the root are mirror image of each other. That's exactly where we use our helper function. This call kicks off the recursive comparison between the left and the right sides of the tree, and from there, Ismirror takes care of walking down both sides of the mirror directions, checking for symmetry all the way down. Let's take a look at a couple of examples to see this in action. Given this tree, check if this tree is symmetric around its center. That means the left subtree is a mirror image of the right subtree. First, call asymmetric function passing the root node 1. Asymmetric in turn call Ismirror function with the left subtree and the right subtree of node 1. F2 to compare this node and this node of the two trees, and since they are the same, continue. Compare the left child of left tree with right child of right tree, and compare right child of left tree with left child of right tree. F3 tree compare this node and this node of the two trees. Their values are the same, so continue. Compare the left child of first tree with the right child of second tree, and the right child of the first tree with the left child of the second tree. All of these four nodes are none, so we have F, none, none, and F, none, none. If both nodes are none, that means we've reached the ends of both sub-tree at the same time, and everything's matched so far. Return true. Similarly, F44 continue checking the subtree of this node and this node on the opposite direction. This one go left, then this one go right, this one go right, and this one go left. And of course, they're all none. So return true. No more function calls at this time, so return the combined result true. Let's take a look at another case. Initially call asymmetric function passing the root node value 1. Asymmetric will call Ismirror passing the left and the right nodes as parameters. F2 to compare these two nodes. Their values are the same. Continue. Compare their subtrees in the opposite direction. Compare left of this tree with the right child of this tree, F none 3. And compare the right child of this two with the left child of this two, F3 none. F none 3 falls into case 2. One node doesn't exist, return false. And since we have the AND operator in our return, so we have early termination, we do not need to proceed any further and return false. So what's really happening here? We walk down both sides of the tree at the same time, comparing opposite positions. If both nodes are none, keep going. If only one node is none, or if their values don't match, stop right away and return false. If all pairs not pass this check, then the tree is symmetric. Alright, time to smash the submit button. Boom, accepted. So that's how the recursive asymmetric function works. A clean, elegant solution that shows how recursion can naturally handle these kinds of tree comparison. If you found this helpful, check out other binary tree videos on the channel. We cover traversal techniques, tree comparisons, and more. I'm Alan. Thanks for watching. Welcome back to Leetcode Simplified. I'm Alan, and today we're walking through Leetcode 104, maximum depth of binary tree. Given the root of a binary tree, return its maximum depth. In other words, calculate the number of nodes along the longest path from the root node down to the farthest leaf node. Let's walk through the elegant, short, recursive approach. First, if the node is none, return 0. No node, no depth. If the node does exist, return 1 for this node. Adds to the depth. This might not be a leaf. We need to go deeper. Do that by recursively calling the same function on the left child and the same on the right child. Then take the larger of the two because we want the longest path and add it to the result. What we're doing is we walk down the left and right subtree of the current node. We hit a none, then return 0. We reach the bottom. If we hit a real node, return 1 plus the maximum depth from its left and right subtrees. Take a look at the example on the left with the given the root node value 3. First, call max depth passing the root node 3. F of 3 will return 1 plus max of f of 9 and f of 20, the left and the right subtree of node 3. F of 9 return 1 plus max of its left and right subtree, which is 0 because node 9 is a leaf, no left subtree or right subtree. F20 return 1 plus the max depth of its left subtree F15 and depth of its right subtree F7. F15 return 1 plus max depth of left and right, which are both 0. Similarly, F7 return 1 plus the max depth of its left and right, which are both 0. Let's write everything down all together. So 3 is the total of nodes along the longest path from the root down to the farthest leaf node. Alright, time to smash the submit button. Boom, accepted. So that's how the recursive max depth function works. Base case return 0 if the node is none. Recursive case return 1 plus max depth of left and right subtrees. Clean, efficient, and a favorite in coding interviews. If you found this helpful, check out the other binary tree videos on the channel. We cover traversal techniques, tree comparisons, and more. I'm Alan and this was Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan. Today we're walking through Leetcode 111, minimum depth of binary tree. Given the root of a binary tree, return its minimum depth. In other words, calculate the number of nodes along the sorted path from the root down to the nearest leaf node. We will use recursive approach, which is elegant, short, and often asked in interviews. When recursively go down the tree from the given root node, we might encounter 4 cases. Case 1. If the node is none, return 0. No node, no depth. Case 2. If the node is a leaf, meaning it has no left child and no right child, then return 1, the node itself. Case 3. If the node only has one child, let's say it has no left child, then we need to return 1 to count itself plus the min depth of its right subtree. Same logic applies if it has no right child. Return 1 to count itself plus the min depth of its left subtree. Let's say node 3 don't have left child. Then at node 3 the function will return 1 plus the min depth of node 20, the right subtree. We don't take the min of left and right. If left is missing, it's not a valid path. Case 4. If the node has both left and right child, return 1 for the node itself plus the smaller min depth of the two subtrees. So what's happening overall as we go down the tree? At each node, 4 cases can happen. If the node is none, return 0. If the node is a leaf, return 1. If the node has only one child, return 1 for the node itself, plus the min depth of its only subtree. If the node has both children, return 1 for the node itself, plus the shorter min depth of its two subtrees. Let's look at the example on the left. First, call the min depth function passing the given root node 3, f3. Let's move it out the way. f3 will return 1 and the smaller of its sub3 min depth f9 and f20. f9, the min depth at node 9, return 1 for the node 9 itself because it's a leaf. f of 20, the depth at node 20, return 1 for itself, plus the min depth of its left subtree f15 and its right subtree f7. Min depth at node 15, f15, return 1 for node 15 itself. Similarly, the min depth at node 7, f7, return 1 for node 7 itself. Let's bring everything down to one row. Final outcome is 2. As you can see, there are 2 nodes on the shortest path from the root down to the nearest leaf node. Alright, it's time to smash the submit button. Boom, accepted. That's the recursive solution to the minimum depth problem. It's handled missing children correctly. If you found this helpful, check out the other binary tree videos on the channel. We covered traversal techniques, tree comparisons, and more. Hello everyone, welcome back to Leetcode Simplified. I'm Alan, and today we're walking through Leetcode 108, convert sorted array to binary search tree. This is a classic problem where recursion really shines, and we're going to keep our solution clean, efficient, and balanced. Let's dive in. Given a sorted array of integers in ascending order, convert it to a height balanced binary search tree. Height balanced means the depth of the left and right subtrees of every node differ by no more than 1. Our goal is to split the array in a way that keeps the tree balanced. Since the array is sorted, the middle element should be the root. That way, everything on the left becomes left subtree, and everything on the right becomes right subtree. Repeat this process recursively to build the entire tree. This divide and conquer strategy ensures balance because we're always picking the midpoint. Now let's look at the code in detail. First, if the passed-in array is empty, no more elements to process, we return none to indicate that this branch of the tree ends here and doesn't create a node. Otherwise, we're going to find the midpoint index and create a node with the middle value. Make it root of this subtree. Recursively build the left subtree using all values before the root. And recursively build the right subtree using all values after the root. Finally, we return the root node of this subtree, which connects the whole thing together. This allows the recursive calls to connect everything together and build the full binary search tree from the bottom up. Now let's take a look at the example on the left. Convert the sorted array -10, -3, 0, 5, 9 to height balanced binary search tree. Let's go ahead, run the function passing on this array. Take the middle element and build a node with its value. Make it the root of the left subtree and the right subtree. For the left subtree, we call the function again, passing all the elements before 0. For the right subtree, do the same, call the function itself, passing all the elements after 0. Repeat the same process with the two new arrays, the left array and the right array. Get the middle element and create a node with its value. Make it the root of a tree. Same thing for array 5, 9. Get the middle element and create a node with its value. Make it a root node of a tree. On the left side we have f of minus 10 and f of none. On the right side we have f of 5 and f of none. Minus 10 is the middle element of a single element array. Create a node out of it and make it a root of a tree. 5 is the middle element in a single element array. Make a node out of its value and make it a root of a binary tree. Left of minus 10 is an empty array. Remember, if not nums, return none. So we return none. The right of minus 10 is also an empty array. F of empty arrays return none. Bubble up the result. Finally, we return the root. And there you go. We just convert a sorted array to a height balanced binary search tree. Alright, time to smash the submit button. Boom! Accepted. And just like that, we build a perfect balanced binary search tree. Time complexities of this solution is O of n because we visit every node once. Space complexity is also O of n due to recursion stack and new tree nodes. This is about as efficient as it gets for tree construction from a sorted array. So that's the recursive solution to Leetcode 108, convert sorted array to binary search tree. It's clean, balanced, and leverage the sorted property perfectly. If you found this helpful, check out the other binary videos on the channel. We cover traversal, symmetry checks, and more. I'm Alan, and this was Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan, and today we're walking through Leetcode 110, Balanced Binary Tree. Given the root of a binary tree, determine whether the tree is height balanced. That means for every node in the tree, the heights of its left and right subtrees differ by no more than 1. This single node tree is balanced. This single node tree is balanced. Its height is 1. Its height is also 1. The tree at root node 20 also balanced because the height of its left and right subtree differ by no more than 1. Its height is 2. This single node tree of course is balanced. Its height is 1. The tree at root 3 also balanced because the height of its left and right subtree differ by no more than 1. Its height is 3. How about this tree? A single node tree is always balanced. Height is 1 and 1. The tree at root node 3 also balanced because heights of its left and right subtree differ by no more than 1. Its height is 2. This single node tree is balanced. Its height is 1. This tree at root node 2 also balanced because heights of its left 2 and right 1 differ by no more than 1. Its height is 3. This single node tree is balanced. Its height is 1. The tree with root node 1 is not balanced because the height of its left right differ by 2. Here's the idea. Use a bottom-up recursive approach. Write a helper function that runs at every node and does two things. Returns -1 if the subtree rooted at that node is not balanced. Otherwise, it returns the height of that subtree as we see on the left. Let's translate this idea to Python. First, define the recursive helper function check node to be called at every node. This function will return -1 if the current tree is unbalanced or its actual height if balanced. If current node is none, means no tree, no height, return 0. It's our recursive base case as we can see all 0 on the left. Otherwise, if it's a real node, recursively check the left subtree, then recursively check the right subtree, and save their result into variables left, right. If either subtree is unbalanced, meaning it returns -1, or the difference in their heights is more than 1, then the current subtree is unbalanced and we return -1. Otherwise, we return the height of the current subtree. So again, helper function check node return -1 if that subtree is unbalanced or its actual height is balanced. If the whole tree is balanced, result at check at the root won't be -1, so we return true. Let's take a look at the lab example step by step. Is the tree with root node value 3 balanced? It will call the check function to find its height or return -1 if the tree is unbalanced. F of 3 will return 1 plus max of its left f of 9 and right f of 20. F of 9 return 1 plus max of f of none and f of none, its left and right subtrees. If not, node return 0, so f none is 0, so the whole evaluation return 1. Similarly, on the right, f of 20 return 1 plus max of f of 15 and f of 7. Just like f9, the result is 1. F15 and F7 result also 1. The height difference between F15 and F7 is 0, so return the total evaluation would be 2. The height difference between the left and the right is no more than 1. Continue processing with the total evaluation. Let's copy everything down to one line. The result of f of 3 is 3. Different than -1, so this evaluation return true. This tree is balanced. How about this tree? The only difference here is F7 return 1 plus max of 0 and 1. This whole evaluation return 3, and the height of the left and right subtree differed more than 1, so we return -1. So F3, instead of returning this, it returns -1. -1 is not different than -1. The whole evaluation return false. So this tree is not balanced. Alright, time to smart a submit button. Moment of truth. Boom, accepted. This solution is both elegant and efficient. Time complexity big O of n because we visit each node exactly once. Space complexity also O of h, where h is the height of the tree due to the recursion stack. And that's it. This is a clean recursive pattern that shows up in many binary tree problems. Check something at the children, bubble up a signal if something goes wrong, and return useful data if not. If you found this helpful, be sure to subscribe to the channel for more Leetcode walkthroughs like this one. I'm Alan and this was Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're walking through Leetcode 112, path sum. Given the root of a binary tree and an integer target sum, determine if the tree has any root to leaf path such that sum of all node values along the path equals target sum. This is a fundamental binary tree problem that teaches how to use recursion to check for a specific condition. In this case, whether a path from root to leaf adds up to a target sum. Here is our approach. We recursively explore its path from the root down to its leaf. At each step, subtract the current node's value from the target sum. At some point, when the node is none, return false. When the root is a leaf node, check its values against the remaining target sum. If not equal, return false. If equal, that means the sum of all node values along this path equals to the target sum. Return true. If we clear on the logic, let's make it happen in Python. If the root is none, that means the tree is empty, no path exists. Return false. If the current current node is a leaf, check if its value equals the remaining target sum. Otherwise, recursively check the left subtrees and right subtrees, subtracting the current node's value from target sum. If either subtree returns true, then there's a valid path that adds up to the target sum. Let's walk through the example on the left step by step. Is this tree with root 5 has a root to leaf path that sum up all values along the path equal 22. F5 22 will check with its left subtree passing on the reduced target sum or its right subtree. F4 17 will check its left subtree or right subtree with the reduced target sum. F9 13 return false because if not root return false. F11 13 check its left and right subtree with the reduced target sum. F7 2 will check its left and right subtree with the reduced target sum. If not root return false. This one return false. So is this one. Since node 7 is a leaf, this function will check if 7 equals the remaining target sum 2. So return false. F22 is similar to F72, but node 2's values equal the remaining sum 2. So the evaluation return true. Bubble it up, false or true, return true. True or false, return true. Whatever on the left side right here, we don't care. True or whatever, return true. There is a path from root 5 to leaf 2, such that adding all values along the path equal 22. Alright, it's time to smash the submit button. Boom! Accepted. This problem is a classic example of using recursion to explore all possible paths in a tree. It's also a great exercise in managing state. In this case, reducing the target sum as we go deeper down the tree. Time complexity is O of n, where n is the number of nodes in the tree. In the worst case, we might have to visit every node once. Space complexity is O of h, where h is the height of the tree. This comes from recursion stack. In the worst case of a Sqrt tree, h could be n. In a Palindrome tree, it would be log n. If you found this helpful, be sure to subscribe to the channel for more Leetcode walkthrough like this. I'm Alan and this was Leetcode Simplified. Thanks for watching. See you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're tackling Leetcode 118 Pascal triangle. We'll learn how to construct the first 5 rows of Pascal triangle like this. I'm going to copy it and put it right here. In Pascal triangle, each number is the sum of the 2 numbers directly above it. In other words, each number is the sum of the above left number and the number directly above it. Let's say if we want to calculate the value at row I, column J. It is the sum of the left above number and the directly above number. This is above left. Let's implement with Python to construct the first 5 rows step by step. Create an empty array to store each row. For each row from 0 to 4. Create an array filled with ones. Row 0 has 1, 1. Row 1 has 2 ones. Row 2 has 3 ones, and so on. For every number from column 1 to the second to last column, update it with sum of above left number and the directly above number. Once done with a row, append it to the triangle array before continue processing to the next row. Finally, once all the rows complete, return the triangle array, which contains us 5 rows of the Pascal triangle. So instead of 5, we can generalize by change to num row. Alright, time to smart the submit button. Boom, accepted. This problem is a classic example of building arrays dynamically using nested loops. It also teaches us how to carefully index into previous data structures to build new ones. Time complexity is big O of n square. N is number of row because we build each row and update elements inside it. Space complexity also is O of n square as well, since the triangle stores all rows. If you found this helpful, be sure to subscribe to the channel for more Leetcode problem walkthroughs like this. I'm Alan, and this was Leetcode Simplified. Thanks for watching. I'll see you in the next one. Hello everyone, welcome back to Leetcode Simplified. I'm Alan. Today we're tackling Leetcode 119, Pascal Triangle 2. We learn how to construct the 4 rows of the Pascal triangle in place. In Pascal triangle, each number is the sum of the 2 numbers directly above it. All rows begin with 1. What's go here? It's the sum of 2 numbers directly above it. 1 plus nothing equal 1. What's go here? Sum of 2 number above it. 1 plus 1 equal 2. Next, 1 plus nothing is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus nothing is 1. Next, 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus nothing is 1. We want our function to return row 4 only. First, we're going to initialize row 4 with all 5 ones. After rounds of going through each column, we modify row 4 in place and return it. For each row, update the row from the second to last column going right to left so we don't override values we still need for calculation. Each element of the row becomes the sum of the element above left and the element directly above, preserving correct values as we go. We can also write this more compactly. Instead of just the 4th row, we can generalize this by replacing 4 with row index to generate any row of the Pascal triangle. Take a look at the diagram to see exactly how our code plays out. We skip I equals 0 and I equal 1 because no element gets changed in the row 4. So we can start from row 2. See nothing changed when I is 0 or 1. Jump straight to I equal 2. At this point, our row looks like 1, 1, 1. Now we update it from right to left, starting at the second to last position. Each element becomes the sum of itself and the one to its left. That gives us 1, 2, 1, with the exactly Pascal triangle row 2. Next, move to I equal 3. Our row start is 1, 2, 1, 1. Again, we go right to left. First update. 2 plus 1 equal 3 and 1 plus 2 equal 3. Finally, I equal 4. Row start at 1, 3, 3, 1, 1. Now, right to left. 3 plus 1 equal 4. 3 plus 3 equal 6. 1 plus 3 equal 4. And boom! 1, 4, 6, 4, 1. Row 4 complete. So initially this row has all 1. After the 4 loops, this row returns this. And that's it. It's time to smart the submit button. And boom, accepted. This problem is a great example of in-place array updates to save space. Time complexity big O of k square because we update multiple positions for each row. We build k's number of row. Space complexity big O of k because we only store a single row instead of the entire triangle. If you found this helpful, be sure to subscribe to the channel for more Leetcode problem walkthroughs like this. I'm Alan and this was Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're solving Leetcode 121. Best time to buy and sell stock. Given a list of daily price of a given stock, find the maximum profits you can make by buying on one day and selling on a later day. For example, given a list of prices, if you buy at price 1 and sell at price 6, your profit is 6 minus 1 or 5. The maximum possible profits you can achieve. Look easy for this list, right? But what if the given list have thousands of prices? Here's the cleanest, most optimal solution to find the max profit in just one pass through the list. Read each number. If it's smaller than the current minimum, update the current minimum to it. Otherwise, subtract it to the current minimum. If the result exceeds the current maximum profit, update the maximum profit to this difference. To implement this, we keep two variables, current minimum price and current maximum profit. Both get updated as we go through each price. Let's code it up. First, set min price to infinity so any price we see will be less than it initially. Set max profit at 0, no profit yet. Then for each price in the list, if it's less than our current min price, we update min price because this price is better to buy. Otherwise, if the price is bigger than the current min price, then subtract it to the current min price, and if the difference is bigger, update the current max profit accordingly. By the end of this loop, max profit holds the maximum possible profit. Look at the list on the left. Initially, min price is set to infinity and max profit is set to 0. Min price and max profit will be updated accordingly when we go through each price in the list. Price 7 is smaller than infinity, then we update min price to 7. At price 1, it's much better than 7 current min price, so update min price to 1. The next day, price is 5, which is larger than the current min price 1. So the profit is 4. Update the current max profit variable to 4. The next day, the price we encounter is 3, which is larger than the current min price 1. So we subtract it to the current min price to find the profit 2, which is not greater than the current max profit 4. So keep 4. The next price is 6, greater than the current min price 1. Subtract the current min price to find the profit. 5 is greater than the current max profit 4, so update max profit to 5. The next day price is 4, greater than the current min price 1, so subtract 1 from it to find the profit. 3 is not greater than the current max profit 5, so we just keep max profit as 5. No more price to read. Max profit holds the maximum profits you can achieve with this list. Alright, time to submit our code. Boom! Accepted. And that's it. A simple, elegant solution to find the max profit. We only pass through the list once, so it's big O and time complexity. We use only two variables, so it's O of 1 space complexity. If you found this helpful, be sure to subscribe to the channel for more Leetcode problem walkthroughs like this. I'm Alan and this was Leetcode Simplified. Thanks for watching. Hello everyone, welcome back to Leetcode Simplified. I'm Alan and today we're tackling Leetcode 136 single number. Given a non-empty array of integers, every element appears twice except for one. Find that single number. For example, 1 is the single number in this array, and 4 is the single number in this array. Because every other number appears twice, the problem asks us to implement a solution with the big O of n time complexity and big O of 1 space complexities. We can't use solutions like counting hash map or using extra memory. Instead, we're going to use XOR operator to solve this problem in just one pass linear time and using only one variable to store the result. Let's quickly look at XOR bit operation. 1 XOR 1 equals 0. 1 XOR 0 or 0 XOR 1 equals 1. 0 XOR 0 equals 0. From this, we observe three very important properties of XOR that will help in this problem. Any number XOR with itself equals 0. A XOR A equals 0. Any number XOR with 0 stay the same. A XOR B equals B XOR A. XOR is commutative. Order doesn't matter. Using these three properties together, when we XOR all the numbers in the array, every duplicate cancels out to 0 and a single number remains. Understanding the intuitive behind this is a bit tricky, but the actual coding is simple. Let's code it up in Python. First, we need a variable to store the result. Set it to 0 because after XOR with the first number is added into the result unchanged. Which is the number in the array, we XOR it with the current result and update result to hold this new value. After the loop finishes, all the duplicates have cancelled out to 0 and result holds the only number that appeared once. Return result. Now let's take a look in detail at example 2. Here's our array numbers in binary. The first one in a number flips the corresponding bit in the result. When a second one appears in another number, the bit flips back to 0 to cancel them out. At the end, the result is 1, 0, 0. Alright, time to smash the submit button. Boom. Accepted. And that's it. Using XOR, we solve it in linear time with constant space. If you found this helpful, be sure to subscribe to the channel for more LeetCode problem walkthroughs like this. I'm Alan and this was LeetCode Simplified. Thanks for watching. See you in the next one. Hi everybody, welcome back to LeetCode Simplified. I'm Alan and in today's episode we tackling LeetCode 141. Linked list cycle. Given the head of a linked list, determine if the linked list has a cycle. That means there is some node in the list that can be reached again by continuously following the next pointer. For example, the last node -4's next pointer points back to node 2 in the list. To detect a cycle in a linked list, we use Floyd cycle detection algorithm, also called tortoise and hare method, the slow and fast pointer technique. A slow pointer moves one step at a time and a fast pointer moves 2 steps at a time. If there is a cycle, the fast pointer will catch up to the slow pointer at some point. If there is no cycle, the fast pointer will reach the end of the list first, at when we will return false. Think of it like two runners on a circular track. The slow runner jogs steadily, while the fast runner runs laps and eventually catch up to the slow runner from behind. The logic is easy to grasp, and turning it into code is just as straightforward. First, create slow and fast pointers, both pointing to the same node as head pointer. While fast and the next node exit, keep doing these steps. Move slow 1 step forward. Move fast 2 steps forward. Then check if fast points to the same node as slow. Return true. If fast is none, that means it reached ends of the linked list. There's no cycle. Return false. Now visualize the logic step by step with the example on the left. Create slow and fast pointer that point to the same node as head is long as fast and the next node exits. Advance slow 1 step and advance fast 2 steps. Then check if they both point to the same node. If not, repeat the process until they meet. Then we return true. There is a cycle in the linked list. If there's no cycle, fast pointer eventually will point to none without ever meet slow pointer. There's no cycle, so return false. Alright, time to smash the submit button. Moment of truth. Boom. Accepted. With Floyd cycle detection, we get super clean, efficient solution, or end of time, or one of space. Simple logic, powerful result. If you found this helpful, be sure to subscribe to the channel for more Leetcode problem walkthroughs like this. I'm Alan, and this was Leetcode Simplified. Thanks for watching. See you in the next one. Hello everybody, welcome back to Leetcode Simplified. I'm Alan, and in today's episode we're tackling Leetcode 160 intersection up to linked list. Given the heads up to singly linked list, find the intersection node. If no intersection, return none. For example, C1 is the intersection node as we can see in the diagram. If list A's length m is different from list B's length n, then pointer A and pointer B will not reach the intersection node at the same time because they move different number of steps in their first pass. How to make them to reach the intersection node at the same time? Let's say x is the length from head A to intersection node C1 and y is the length from head B to the intersection node C1. If two lists intersect, the shared tail has length m minus x in list A and n minus y in list B. Well, it's the same tail, isn't it? M minus x equal n minus y. Rearranging, m plus y equal n plus x. This tells us that if pointer A traverses m nodes on list A, then y nodes on list B, it will reach the intersection node at the same time as pointer B would traverse n nodes on list B, then x nodes on list A. The special case is when two lists not intersect, then x equal m, y equal n. Pointer A travel m and travel n before reaching none. B travel n and travel m nodes before reaching none at the same time. And when A and B both point to none, return A or B means return none. Alright, let's transpile the idea into Python. First, take care of some obvious cases. If either linked list is empty, return none. Create pointers A and B to point to the same nodes as head A and head B respectively. As long as A and B are different, move A 1 step forward if not n+. Else if n+, A goes to head B, the head of the other list. Similarly, advance B 1 step forward if not the end of the list. Else if it's the end of the list, B goes to head A, the head of the other list. When A and B both point to the intersection node, or none if not intersected, return A or B, doesn't matter. The pointers A and B may reach the intersection node at different numbers of steps in their first pass, but because it traverses both lists in total, they reach the intersection node at the same time, at which we can return either pointer A or B that both point to the intersection node, or none if not intersected. Alright, time to smash the submit button. Moment of truth. Boom. Accepted. This method runs in all m plus n time and use all 1 space. Simple logic, powerful result. If you found this helpful, be sure to subscribe for more Leetcode walkthroughs like this. I'm Alan and this was Leetcode Simplified. Thanks for watching. See you. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and in today's episode we tackling Leetcode 168, Excel sheet column title. Convert column number to Excel's column title. For example, column number is 1, column title is A, 2, B, C, 3, 26, Z, and so on. So we can see that Excel numbering system is a one-index base 26 system. Before we dive into this Excel style system, let's first review our zero-index base 10 system that we are very familiar with. Look at the number 731. From this representation, we learn something very important. 731 modulo 10 gives us the remainder 1, the rightmost digit. Then integer division by 10 to remove that rightmost digit, leaving the remaining number 73. Repeat this process with the remaining number. 73 mod 10 equals 3 to get the next digit. Then 73 integer divide 10 to remove that digit, leaving the remaining number 7 to be processed next. The remaining number 7 modulo 10 gives us the remainder 7, the next digit. And 7 integer divide by 10 equals 0. The remaining number is 0, done. So what we just did is modular gives the rightmost digit and integer division removes it. Repeat to extract all the digits from right to left. Now the Excel's one index base 26 system is similar but with a twist. Digits go from 1 to 26, but our modular 26 produce 0 to 25. So how to fix this difference? Subtract 1 before modulo. Let's shift the number into the 0 to 25 range, so the modulo operation correctly mapped to the letters. So subtract 1 from the column number 731, then modular 26 to get the remainder 2, which correctly mapped to letter C in the alphabet. 730 integer divide 26 to remove the rightmost digit 2, leaving the remainder number 28. Repeat the process with the remaining number 28. Repeat the same process with the remaining number 1. The remaining number now is 0. Done. No more number to process. So we can represent the 731 in the 26 base system as, since we subtract 1 before, now we need to add 1. Column number 731 corresponding column title is ABC. Here's the Python implementation following the steps we just discussed to convert a number to its Excel column title. Start with an empty string column title where we will build the Excel title. We loop until column number becomes 0. Subtract 1 from column numbers because Excel system starts at 1 instead of 0 and our modular operation can produce 0. Column number modulo 26 gives us the remainder. 0 means A, 1 means B, 25 means Z. Use ordinal function order and char functions to convert the remainder into the corresponding letter in the alphabet, building our Excel column title one character at a time. Prepend this character to the column title string because we build characters from right to left. After adding the character to the column title, integer divide column number by 26 to move to the next left character. Repeat this process until the column number becomes 0. Start the final column title. Alright, time to smart the submit button. Moment of truth. Boom, accepted. This method runs in big O of log base 26 of n time complexity because each step we divide the number by 26. and use big O of 1 extra space aside from the output strings. If you found this helpful, be sure to subscribe for more Leetcode walkthroughs like this one. I'm Alan and this was Leetcode Simplified. Thanks for watching. See you in the next one. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and in today's episode we tackling Leetcode 171 Excel sheet column number. Convert Excel column title to its corresponding column number. For example, given column title A, column number is 1, B is 2, Z 26, and so on and so forth. So basically, Excel columns are a base 26 number system, but instead of digits 0 to 25, we use letters A to Z that maps to 1 through 26. What about 27? 27 equal 26 plus 1. 1 means A, but this 26 also means A. The first A is 1. If we increase 1 at a time, it takes 26 times from this A to go to this A, this position. What about another A is in A. For the leftmost A, multiply it with another 26. It means we multiply 26 two times, or 26 times 26. So in short, for A, the rightmost A doesn't get multiplied by 26 at all. It just stays as its value to 1. The middle A gets multiplied by 26 once. The leftmost A gets multiplied by 26 two times. Concatenate all A's letters, meaning adding all their numeric values together, and you get the total column number. What about B? What about A, B, C? You can see the pattern clearly. Each letter's value is multiplied by 26 to the power of its position from the right, starting at 0. When we read each letter from left to right, multiply the current total by 26 each time, then add the letter's numeric value. It automatically handles these powers of 26 for us. Here's the Python implementation following the steps we just discussed to convert Excel column title to its corresponding column number. Initialize column numbers as 0. For each letter in the title from left to right, multiply the current total by 26, then add the numeric values of the current letter. Let's convert the letter into its numeric value. Its ASCII code subtract the ASCII code of letter A, and add 1 because A maps to 1. Update the column number with these new values. Return the final column numbers once all the letters are processed. Alright, let's hit the submit button momentarily through. Boom, accepted. This simple formula works for any length of Excel column title, and the key idea is always multiply by 26, then add the letter's value. Time complexity is big O of n, where n is length of the column title because we loop through each letter once. The space complexity is big O of 1 constant space. We use only single variable column numbers. If you found this video helpful, make sure to subscribe to Leetcode Simplified for more step-by-step walkthroughs. I'm Alan and this was Leetcode Simplified. Thanks for watching. I'll see you in the next one. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and in today's episode we're tackling Leetcode 169, the majority element. Find the majority element that appears more than half of the time in a given array. Guarantee it always exists. For example, number 3 appears 2 times out of 3 elements, more than half. In the next array, number 2 appears 4 times, more than all other numbers combined. So 2 is the majority element. The straightforward way to find the majority element is to count the frequency of each number using a hash map. Whichever number appears the most is the majority element. This works, but it requires extra space, the hash map. we will take a look at a much more elegant solution known as the Boyer-Moore voting algorithm. Here's the key idea. If the majority element appears more than all others combined, then even after subtracting one occurrence for each other element, the majority element's count is still at least one left. Think of the majority element as the election winner. The winner already has more votes than any other candidate combined. Even after subtracting one vote from the winner for each vote other candidates got, the winner still have at least one vote left over. Let's translate this idea into Python. While scanning through the array, keep two variables, candidate for the potential majority element and count for how many votes it currently has. Go through each number. The rules are simple. If count is 0, we don't have a candidate yet. So set the current number as the candidate and set count to 1. The first number we encounter is 2. So we set 2 as the candidate and give it a count 1. Moving on to the next number. If it still equals the current candidate, just increase the count of the current candidate. The current number now is 2, which is still the same as the candidate. So we just increase the candidate's count to 2. Continue with the next number. If it's different from the current candidate, decrease the count of the candidate. We are now at the current number 7, which is different from the candidate number 2. Then decrease the count of the candidate to 1. Next, current number 0, which is different than the current candidate 2. So decrease the count to 0. Next, this time the current candidate got 0 count. Replace candidate with 9. 9 got 1 count. Next number is 2, which is different than the current candidate 9. Then subtract 1 from count. Next, current candidate 9 has 0 count. So replace candidate with the new number 2 and its count is 1. No more number. Loop ends. Return the candidate which points to the majority number because its count is more than all other numbers combined. Even in the worst case scenario, after cancelling out with all the different numbers one by one, number 2's count is still at least 1 left. Alright, time to smart the submit button. Moment of truth. Boom, accepted. This algorithm runs in O(n) of time since we scan the array once, and it uses O(1) of space because we only keep 2 variables. And that's it for today. With the Boyer-Moore voting algorithm, we can find the majority element efficiently without any extra memory. If you found this explanation helpful, don't forget to subscribe and check out the playlist for more Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching. See you in the next one. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and in today's episode, we're tackling Leetcode 190, reverse bits. Reverse bits of a given 32-bit size integer. Well, the first thing might come to mind is the naive approach. Convert the integer into a binary string, and revert the string and convert it back into an integer. This works perfectly, but it's inefficient and involves string operations. Instead, we can do this directly with bit operations. For example, given integer 13, its 4-bit binary is 1101. We demo with a 4-bit integer to keep it simple, but the exact same logic applies to 32 bits. Here's how we're going to reverse number 13 bits with direct bit manipulation in Python. First, create variable result to hold the reverse number. Initialize it to 0. Since this is a 4-bit, we're going to perform the following steps 4 times. Shift result left by 1 bit to make space. and 1 reveals the last bit of n. Then we OR that bit with result to append it to the result. And 1. Anything n with 0 becomes 0. Anything n with 1 stay the same. So 1 here and with 1 will stay the same. Then we OR it with the result to append that bit to the result and update the result. Anything OR with 0 stay the same. So this won't change. Similarly, anything here OR with 0 stay the same. So we update result. Now we shift and write by 1 bit, making the next bit ready for the next iteration. Second iteration, shift result left by 1 bit to make space. And 1 to get the last bit of n to here. And append it to result by OR it with result. Shift and write by 1 bit, making the next bit ready for the next iteration. Iteration 3. Shift result left by 1 bit to make space. And 1 to get the last bit of n. Then OR it with the result to append that bit to the result. Shift and write by 1 bit, making the next bit ready for the next and last iteration. Shift result left by 1 bit to make space. And 1 to get the last bit of n. Then OR it with result to append it to the result. So reverse the bits of 13. We got 1011 or integer 11. For 32-bit integer, the exact same steps apply. Just repeat 32 times. At the end, result contains the reverse integer. Alright, time to smash the submit button. Moment of truth. Boom, accepted. This algorithm runs in big O of 31 time complexity with e constant, so we treat it as big O of 1. And it uses big O of 1 space complexity, since we use only 2 variables, result and n. And that's it for today. We saw Leetcode 190 reverse bits using a clean and efficient bit manipulation approach. If you found this explanation helpful, don't forget to subscribe and check out the playlist for more Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching and I'll see you next one. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and today we'll be solving Leetcode 191, number of 1 bits. Given a positive integer n, return how many set bits ones appear in its binary representation, also known as the Hamming weight. For example, given integer n equal 11, its binary string is 1011, has 3 ones. There are several ways to solve this problem. The first idea most people have is the straightforward one. Convert the integer into a binary string, then simply count the number of ones. Let's submit. Accepted. Great. Simple, readable, and it gets the job done in a different way, equivalently. But we can do better. Instead of working with strings, we can go straight to bit manipulation. That's where the real magic happens. One classic technique is to repeatedly check the last bit of n, then shift n to the right until it becomes 0. Each time the last bit is 1 increment counter. Let's implement that idea. First, initialize count to 0. Until n becomes 0, do n and 1 get 0 or 1 depends on the last bit of n. Add it to count. Then shift and right by 1 bit. Repeat until n becomes 0. At the end, count will be our answer. N and 1 equal 1 or 0 depend on the last bit of n. If the last bit of n is 1, then 1 and 1 is 1. If the last bit of n is 0, then 0 and 1 will be 0. So add this to cow, cow becomes 1. Then we shift and write by 1 bit to make the next bit ready for next iteration. After shifting, repeat n and 1 is 1 plus to cow 2. Shift and write by 1 bit ready for the next step. After shifting, n and 1 is 0. Add 0 to cow still the same 2. Shift and write by 1 bit, get the last bit ready for next iteration. After shifting, repeat n and 1 is 1. Add to cow, cow become 3. Shift and write by 1 bit, n now becomes 0. Loop ends, cow hold the number of 1 bits. Okay, let's submit this version. Alright, accepted. Wonderful. This algorithm runs 32 times for 32-bit integer. And finally, we look at the optimal solution, Brian Cunningham algorithms. Here is the clever trick. Turns the rightmost set bit 1 to 0 until n becomes 0. How? N minus 1 flips the rightmost 1 and all bits to its right. Then n with original n will turn the rightmost 1 of n to 0. Increase cow. N minus 1 will flip the rightmost 1 and all bits to its right. Then end it with the original n will turn the rightmost 1 to 0. Increase cow. Repeat with the new n. N minus 1 flip the rightmost 1 and all bits to its right. Then end it with the original n will turn the rightmost 1 to 0. Increase cow. Repeat with new n. N minus 1 flip the rightmost 1 and all bits to its right. Then end it with the original n will turn the rightmost 1 of n to 0. Increase cow. N now is 0. Loop n. Cow is our answer. As you can see, the number of times it repeats is exactly the number of ones in n. Super efficient and a neat piece of computer history. Alright, time to smack the submit button. Boom, accepted. So there you have it. 3 different ways to solve Leetcode 191 number of 1 bits. If you found this explanation helpful, don't forget to subscribe and check out the playlist for more Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching and I'll see you in the next one. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and today we'll be tackling Leetcode 202, happy number. Given a positive integer, repeatedly replace it with the sum of the square of its digits until it either equals 1, in which case we return true, or it loops endlessly in a cycle, in which case we return false. For example, 19 is a happy number because we repeatedly replace it by the sum of square of its digits and finally it equals 1. Square its digits of 19, 1 square and 9 square. We sum it up become 82. Then square its digit of 82, 8 square, 2 square and sum them up become 68. Square its digits of 68 and sum them up 6 square plus 8 square equal 100. Square its digits of 100, 1 square plus 0 square plus 0 square equal 1. Number 20 is not a happy number because at some point the number 20 repeats again. This means it will cycle forever without reaching 1. Square its digit of 20 and sum them up equals 4. Square its digits of 4 and sum them up equals 16. Square its digit of 16 and sum them up equals 37. Square each digit of 37 and sum them up equal 58. Square each digit of 58 and sum them up equal 89. Square each digit of 89 and sum them up equal 145. Square each digit of 145 and sum them up equal 42. Square each digit of 42 and sum them up equal 20. Back at 20 again. That means it's cycle forever, so 20 is not a happy number. The challenge here is, how do we know that a value was seen before? The idea is simple. Keep a set called scene. Repeatedly put current sum of square of its digits into scene if that sum is not there. If that sum is there, return false. If the current sum equals 1, then return true. Let's dive right into the code. First, create set scene. As long as n greater than 1, do the following steps. If the current sum is in scene, we return false. Else, add the new sum into scene. Now, compute the new sum for the next iteration. For each digit in strings n, convert it to integer and square it. Sum them up, update n with that new sum. Repeat until n either is in scene, in which case we return false, or n equal 1, in which case we return true. Alright, time to smart a submit button. Boom, accepted. The time complexity of this solution is big O of d times k, where k is a number of iterations bounded by a constant. It never grows with n. D equals number of digits of n, or big O of d. Let's calculate d. Let's take a look. In other words, if n has d digits, then it lies between equivalently. So in general, the algorithm runs in big O of log n time. Space complexity is also big O of log n as well, since we use a set to keep track of scene numbers. If you found this explanation helpful, don't forget to subscribe and check out the playlist for more Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching. I'll see you in the next one. Hello everybody, welcome back to Leetcode Simplified. I'm Alan. Today we'll be tackling Leetcode to 63, ugly number. Determine if n is an ugly number, positive integer whose only prime factors are 2, 3, and 5. Mathematically, that means. Let's look at some examples of ugly numbers where the prime factors are only 2s, 3s, and 5s. Ugly number 4 has prime factor 2 and 2. Ugly number 6 has prime factor 2 and 3. Ugly number 15 has prime factor 3 and 5. Ugly number 30 has prime factor 2, 3, and 5. Ugly number 60 has prime factor 2 and 2 and 3 and 5. By definition, 1 is ugly number because 1 has no prime factors. Now, look at some other numbers that are not ugly because they have prime factors which are not 2, 3, or 5. 14 is not ugly because it has prime factor 7. 33 is not ugly because it has factor 11. Again, the rule is clear. Ugly number has only factors 2, 3, and 5. So if we divide n repeatedly by 2, 3, or 5, remove all those factors. In the end, we should get 1 if it's ugly. If not 1, it's not ugly. Let's put Python to work. If n is not positive, it's not ugly. Now we check prime factors 2, 3, and 5 because an ugly number cannot have any other prime factors. As long as divisible, keep dividing n by 2, then 3, then 5. And update n. Use integer division to keep n as an int, not a float. After remove all factors up to 3 and 5 if any, and should be 1 if it is an ugly number. And that's it, clean and simple, perfectly matching the math we discussed earlier. Alright, let's smash the submit button. Boom, accepted. The time complexity is big O of log n because in the worst case we keep dividing n by 2, 3 or 5 until it becomes 1. Each division reduces n, so the number of steps grow roughly with the logarithm of n. Space complexity is constant big O of 1 because we use only variables n and p, so the memory usage stays constant regardless of the input side. That's it for today. If you found this explanation helpful, don't forget to subscribe and check out the playlist for more Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching. I'll see you in the next one. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and today we will be tackling Leetcode 507, perfect number. Determine if n is a perfect number, a positive integer that is equal to the sum of its positive divisors, excluding the number itself. Let's look at the perfect number 28. What are the divisors of 28? 1, 2, 4, 7, 14. Sum all the divisors of 28 equals 28. What are the divisors of 6? 1, 2, and 3. Sum all the divisors of 6 equals 6. So 6 is a perfect number. What are the divisors of 8? 1, 2, 4. Sum of all divisors of 8 does not equal 8. 8 is not a perfect number. So the rule is clear. We need to find all divisors of n except n itself. Sum them up and check if the sum equals n. Because divisors come in pairs, if d is a divisor of n, then n divided by d is also a divisor. For example, 2 is a divisor of 28, then 28 divided by 2. 14 is also a divisor. 4 is a divisor of 28. Then 28 divided by 4. 7 is also a divisor. 2 is a divisor of 6. Then 6 divided by 2. 3 is also a divisor. So only check divisors up to square root of n because every divisor below square root of n has a partner above square root of n. By the time we reach square root of n, we already found all divisors. Let's implement our logic in Python. First, number 1 is not a perfect number because sum of its proper divisors is 0, not 1. Initialize a variable to keep track of the sum of divisors. Start with 1 since 1 is a divisor of every integer. Now we're going to check for potential divisors from the range 2 to square root of n. If divisor divides n evenly, add both divisor and divide divisor to sum. We use integer division to make sure we're adding whole numbers, not floats. At the end, check if n equals sum of its divisors. Okay, let's submit this version. Boom, accepted. This code works 100% correctly, even though perfect square like 9, 16 or 25, the square root is added twice in the sum. For example, the sum of divisors of 9 becomes 1 plus 3 plus 3, which is not the true sum, 1 plus 3. However, for the purpose of perfect number checking, this doesn't cause wrong result because no known perfect number is a perfect square. If you want a version that is 100% technically correct, just check if n is a perfect square. If it is, add only the divisor once, since divisor equals n divide divisor. If n is not a perfect square, add both divisor and its pair. Alright, let's try it. Submit. Boom. Accepted. And that's it. Clean and simple. perfectly matching the math we discussed earlier. The time complexity is big O of square root of n because we only check divisors up to square root of n, which is much faster than checking all numbers up to n. And the space complexity is constant big O of 1 since we only use variable n and sum. If you found this explanation helpful, don't forget to subscribe and check out the playlist for more Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching. I'll see you next one. Hello everybody, welcome back to Leetcode Simplified. I'm Alan. Today we will be tackling Leetcode 203, remove linked list elements. Given the head of a linked list, remove all the nodes whose values equal target. Return the new head. The core logic here is simple. When we are at a node before the target, we skip the target by pointing the next pointer to the node after the target. And a special case happens if the head equals the target. A simple solution is to use a dummy node before the head so that we always have a node before the head. Let's walk through step by step in Python and visualize it on the diagram how we can rewrite the linked list to implement this logic. First, create a dummy list node. Create two pointers called dummy and cur pointing to this dummy node. Pointer dummy doesn't move. Pointer cur actually traverses the list. Connect dummy node to the given head node of the linked list. Now, cur traverses the linked list and look ahead with cur next. As long as it's not none, do. If the next node is not the target, simply advance cur. The next node is not the target, advance cur. If the next node is the target, then point cur next to the node after the target. Curve next value is 3, not the target, advance cur. Curve next value is now 4, not the target, advance cur. Curve next value is now 5, not the target, advance curve. Curve next value is now 6, the target. Point curve next to the node after the target. Curve next is now none. Curve currently is at the end of the linked list. Return dummy next as the new head of the linked list 1 to 2 to 3 to 4 to 5. Special case when head equals target 6. With this setup, luckily we always have a dummy node before the head. Then if heads need to be removed, just point curve next to the node after head. Everything else is the same. Next node not target, advance. Next node target, skip. Next node target, advance. Next node target, advance. Next node, none. Return dummy next. And there you have it. Remove linked list elements using dummy node to handling special case. Alright, time to smart the submit button. Boom! Accepted. The time complexity is linear, big O of n, since we traverse its node once. Space complexity is constant, big O of 1, since we only create a dummy node with two pointers, dummy and curve. That's it for today. If it's helped, please subscribe and check out the playlist for more step-by-step tutorial like this one. I'm Alan and this was Leetcode Simplified. See you next time. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and in this video we going step by step through Leetcode 206, reverse linked list. Given the head of a singly linked list, reverse it and return the head of the reverse linked list. This is one of the most fundamental linked list problems and a very popular interview question. Once you understand it, a lot of other linked list problems become much easier. The key challenge here is how to reverse a next pointer without losing the connection to the rest of the list. We use three-pointer approach. Set up 3 pointers, brief, curve, and next. Flip curve next to point to brief, then advance brief, then advance curve, then advance next as well. Repeat these steps until we've gone through the entire list. Let's dive right into Python and visually trace the algorithm on a diagram step by step. Set up brief pointer pointing to none. Set up curve pointer pointing to head. As long as a curve is not none, keep iterating the following steps. Set up an xt pointer pointing to the next node. Reverse curve next pointer by pointing it to brief. Advance brief. Advance curve. Repeat these steps until curve is none. First advance next. Second reverse curve next. Third advance brief. And lastly advance curve. Curve is not null. Repeat. First advance next. Second flip curve next. Third advance brief. And lastly advance curve. Curve is not none. Repeat. First advance next. Second reverse curve next. Third advance brief. And lastly advance curve. Curve is not none. Repeat. First advance next. Second reverse curve next. Third advance brief. And lastly advance curve. Curves now point to none, meaning brief is at the end. Return brief is the head of the reverse list. And that's it. We successfully reversed the linked list with the simple 3-pointer approach. Submit. Here's come the moment of truth. Boom. Accepted. The time complexity is linear, big O of n, since we go through each node once. Space complexity is constant, big O of 1, since we only create 3 pointers. If you found this explanation helpful, don't forget to subscribe and check out Leetcode playlist for all the Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching. I'll see you in the next video. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and in this video we go step by step through Leetcode 205 Isomorphic Strings. Given strings S and T of the same length, determine if they are isomorphic, meaning every occurrence of a character in one string must map to the same character in the other string. For example, given string S A B C B A and string T X Y C Y X, every occurrence of A must map to X and vice versa. The order must be reserved. For example, A appears at index 0 and 4, so A is X. No two characters may map to the same character. That means its mapping is unique. And a character may map to itself. For example, C mapping to C. As you can see, this is a one-to-one mapping. To solve this, use two dictionaries. Dict1 to map characters from S to T, and Dict2 to map characters from T to S. Loop through both strings at the same time and check the mapping rules. If any conflicts, return false, otherwise return true. Let's dive right into Python and see it in action step by step. Create two dictionary Dict1, Dict2 to check which characters from S map to which character in T and which in T map to which in S. Now loop through a pair of characters in both strings in the same position. If character from S is in Dict1 and it is already mapped to a different characters in string T, that violates one-to-one mapping. Return false. Similarly, if character from T is in Dict2 and it is already mapped to a different character in S, that violates one-to-one mapping rule. Return false. If there's no mapping yet, or if a mapping already exists but doesn't conflict, we store the current pair in both dictionaries. Repeat. Go through the next pair. No mapping yet, so we store the next pair in both dictionaries. Go to the next pair, C to C, not in the mapping yet, so add to both Dict1 and Dict2. Next pair, B, Y. The mapping B to Y, Y to B already exists in both dictionaries. Since there are no conflicts, simply move on to the next pair. Next pair, A and X. Mapping for A to X and X to A already exists in both dictionaries. Since there are no conflicts, move on. If we finish the strings with no mapping conflicts, the strings are isomorphic, so we return true. And that's it. We successfully implement the isomorphic string check. Let's submit the code. Here comes the moment of truth. Boom! Accepted. The time complexity is linear big O of n because we process each character once. And the space complexity is constant big O of 1 because the dictionary stores at most 256 character mappings. If you found this explanation helpful, don't forget to subscribe and check out my Leetcode playlist for all the Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching. I'll see you in the next video. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and in this video we'll be solving Leetcode 217 contains duplicate. Given a list of numbers, return true if the list contains any duplicate and return false otherwise. Super easy. We know that sets automatically remove any duplicate from the list, so convert our list to a set. If there's some duplicate in the list, the length of the set will be smaller than the length of the original list. Let's copy it over here. Okay, submit. Done. We successfully check if the list contains any duplicate. But wait, this approach goes through all numbers in the list to build our set. We don't want that. We want to stop immediately when we see the first duplicate. Here's the optimized approach. First, create an empty set scene. Now, loop through list nums. As soon as we see the first duplicate in set scene, stop immediately and return true. Otherwise, add the current number into set scene. If we reach the end of the list, that means no duplicate found. Return false. That's it. Easy. The moment we see a duplicate, exit right away and return true. Alright, let's mark the submit button. Here's come the moment of truth. Boom! Accepted. Time complexity is linear, big O of n average, but can be faster in practice because it stops immediately when a duplicate is found. Space complexity is big O of n because we store numbers in a set. That's it for today. If you found this explanation helpful, don't forget to subscribe and check out my Leetcode playlist for all the Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching. I'll see you in the next video. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and in this video we'll be tackling Leetcode 219 contains duplicate 2. Given a list of numbers and an integer k, return true if the list has duplicates within k distance. For example, within a distance of 1, 2, 3, number 1 appears twice, so we return true. Next example, within distance of 1, number 1 appears twice, so we return true. Now look at the last example. Within a distance of 1, 2, there's no duplicate, so we return false. We could use brute force to check all pairs of indices, but that's big O of n square, definitely way too slow. Instead, we can optimize using a sliding set of size at most k. As we loop through the numbers, if a new number is already in the set, we found a duplicate within k distance and can return true immediately. If it's not in the set, we add it, and if the set grows beyond size k, remove the oldest number to keep window size in check. Okay, let's turn this logic into Python step by step. First, initial an empty set called scene. Next, loop through the numbers in the list using their indices. If the number is already in the set scene, that means we found a duplicate within k distance, return true. If it's not in the set scene, add it to scene. Add 1 to scene. Next number 2 is not in scene, add to scene. Next number 3 is not in scene, add 3 to scene. Next, number 1 is already in set scene. That means we found duplicate 1 within 3 distance. Exit the loop and return true. Let's look at example 2. Create an empty set scene. Loop through numbers in the list. Number 1 is not in the set, add 1 to the set. Next number, 0 is not in the set, add 0. Now, if set scene has more than k elements, remove the oldest element to make sure the set contains only the last k numbers. The set now has 2 elements greater than k1. We need to remove the oldest element from the set. Next, number 1 is not in the set, added to the set. The set now contains 2 elements which is greater than k1. We need to remove 1 element from the set. Next number, 1 is already in the set. We return true. Let's take a look at example 3. First, create an empty set. Now go through the numbers in the list. Number 1 is not in the set, add 1 to the set. Next number 2 is not in the set, add 2. Next number 3 is not in the set, add 3. The set now contains 3 elements greater than k2. Remove the oldest element from the set. Next element 1 is not in the set, add 1. The set now has 3 elements greater than k2. We need to remove the oldest element from the set. Next element 2 is not already in the set, add 2. Again, the set now has 3 elements. We need to remove the oldest element. Next element 3 is not already in the set, add 3 to the set. The sets now have 3 elements greater than k2. Remove the oldest element from the set. No more element to loop through. If the loop finishes without finding any duplicates within k distance, return false. Done. Super clean and efficient. Let's double check everything. I spotted a tiny typo. Scene, not C. Alright, let's mark the submit button and boom, accepted. The time complexity is big O of n because each number is added and removed from the set at most once. The space complexity is big O of k because the set store at most k elements. That's it for today. If you found this explanation helpful, don't forget to subscribe and check out my Leetcode playlist for all the Leetcode problems explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching and I'll see you in the next video. Hello everybody, welcome back to Leetcode Simplified. I'm Alan and in this video we're going to solve Leetcode 222. Count complete tree nodes. Given the root of a complete binary tree, count the number of the nodes in the tree. According to Wikipedia, a complete binary tree means every level is completely filled except the last level, which can be filled from left to right. Design an algorithm that runs faster than big O of n time complexity. Big one, this is not an easy problem despite what Leetcode says. We need to fully understand the properties of complete binary tree and perfect binary tree to come up with an algorithm faster than big O of n time. Let's start with the easy, straightforward recursive solution which runs in big O of n time. If root is none, return 0 count. Otherwise, count the root itself as 1, plus the node count in the left subtree, plus the node counts in the right subtree. Done. Easy solution. Let's submit this easy peasy not so crazy solution. Boom. Accepted. This works. But it's big O of n time complexity. Too slow for large trees. The problem wants an algorithm that runs faster than big O of n time complexity. Let's improve with a much faster solution using the fact that a complete binary tree can also be a perfect binary tree. First of all, we need a helper function to compute the height of a complete binary tree. Initiate the height as 0. Because complete binary tree is filled from left to right, we can compute its height by going all the way left until the node is none. Increase the height along the way. H will be the height of the tree. So what is the height of this tree? 1, 2, 3. What is the height of this tree? 1, 2. What is the height of this tree? 1, 2. Again, the height of a complete binary tree can be computed by counting the nodes along the leftmost path, since the tree is always filled from left to right. Now back to our main function's logic. If root is none, return 0 count. Compute the height of the left and right subtree. Here is the crucial deduction we need to understand. If left subtree height equals right subtree height, that means left subtree must be a perfect binary tree. Return 1 count for the root plus the number of nodes of that left perfect binary tree plus the count of nodes on the right subtree. If the left subtree height is larger than the right subtree height, that means the right subtree must be a perfect binary tree. For example, if the blue right subtree don't have this node, then the blue right subtree is perfect. Return 1 for the root count plus the number of nodes of the blue right perfect binary tree plus the count on the red left subtree. Again, let me emphasize this very crucial deduction. Look at the yellow tree. If the red left subtree height equals the blue right subtree height, then the red left subtree must be a perfect binary tree. Otherwise, the blue right subtree must be a perfect binary tree. Why? Because a complete binary tree is always filled from left to right. So the left subtree gets completely filled first before the right subtree even starts. Oops, I see a small indentation error. Let's correct it. Okay, that looks great now. And we're done. But it's not easy at all. Alright, time to submit our code. Here's come the moment of truth. Boom, accepted, great. So computing the height takes big O of log n. And we do this up to log n times. So the total is log n times log n, much faster than big O of n. That's it. We solved Leetcode 222, count completely 3 nodes using an easy recursion depth first serve, big O of n solution, and a not so easy solution but optimize big O of log n times log n using a complete binary tree and perfect binary tree properties. If you found this explanation helpful, don't forget to subscribe and check out my other Leetcode playlist, explained simply and clearly. I'm Alan, and this was Leetcode Simplified. Thanks for watching, and I'll see you in the next video.